Hello and welcome to Simply About Earth. I'm really glad you made it here tonight. Wherever you are in the world, tucked in bed, resting after a long day, or simply searching for a quiet corner, this little space is for you. A place where calm and curiosity can meet side by side. Tonight, we'll wander back into a chapter of Earth's past that feels almost impossible to imagine. A story about a mountain that once tried to erase us. 74,000 years ago, in the heart of what is now Sumatra in Indonesia, a volcano named Toba erupted with a force beyond imagination. This was no ordinary eruption. It was an open wound in the planet's crust, a blast so vast that every other volcanic disaster in recorded history seems small beside it. More than 2,800 cubic kilometers of ash rose into the sky, spreading across continents, blotting out the sun. For days the sound would have rolled across oceans, echoing off the edges of the world. Daylight faded into a dim, unending dusk. Across the world temperatures fell by more than 10 degrees. Forests died where they stood. Rivers froze. Animals perished. Whole regions of Africa and Asia became wastelands overnight. And humanity, fragile, scattered, unprepared, nearly vanished too. Some scientists believe our numbers fell to just a few thousand survivors, a population so small that we came within a breath of extinction. Every face you know, every voice you love, may trace their existence back to the few who endured that endless winter of ash. Before we dive deeper into this story, let me know in the comments where you're listening from tonight and what time it is there. I always love to see how far these quiet ripples reach across the world. But how did they endure in a world determined to erase them? What did survival look like when the air was filled with dust and the night stretched on without warmth? And most haunting of all, if the planet once tried to erase us, what would happen if it tried again? Tonight, we'll follow the trail left behind in rocks, in ice, and even in our own DNA. We'll explore what happened when the skies went dark, how humanity clung to existence, and what this means for us today. So now take a slow breath, let your shoulders relax, and let's begin. When most people think of a volcano, they imagine a mountain that breathes smoke, its peak glowing faintly against the night. Rivers of fire flow down its sides, and the air trembles with the sound of distant thunder. These are the volcanoes that fill history books and myths, the ones that can be seen from afar, living mountains that growl before they strike. But hidden beneath the surface of our planet are far larger forces, so vast that their true shape can only be seen from space or revealed through the patient eyes of science. These are the supervolcanoes, silent giants that slumber for ages, wearing landscapes like masks to hide the restless power below. The word supervolcano describes something beyond imagination. It does not mean a volcano that is simply larger or taller than the rest, but one that is capable of releasing energy on a scale that can transform the entire planet. Scientists use the Volcanic Explosivity Index to rank eruptions by size and impact. The eruption of Mount St. Helens in 1980, for example, ranks at a level 5, powerful enough to flatten forests and darken skies across states. But a supervolcano reaches level 8, the top of the scale, releasing thousands of times more ash, gas, and molten rock than even the most violent ordinary eruption. It is not an event that destroys a region, it is an event that reshapes the world. What makes supervolcanoes especially haunting is how ordinary they appear. They are not the classic pointed peaks crowned with fire. Many are broad depressions in the earth, so wide and shallow that their edges are hard to see from the ground. These great craters are called calderas, the scars left when a past eruption emptied its magma chamber and caused the land to collapse. Over tens of thousands of years, water collects in these basins, forming lakes so calm and reflective that no one standing by their shores would suspect the power sleeping beneath. Forests take root around their rims, and animals wander freely over ancient wounds in the crust. To stand beside Lake Toba in Sumatra or gaze across the vast valley of Yellowstone in North America is to witness serenity that hides unimaginable force. This calmness is deceptive. Beneath these peaceful surfaces lie reservoirs of molten rock that slowly gather over millennia, fed by heat rising from deep within the planet. The process is patient, invisible, and almost soundless. Magma moves upward through fractures, pooling in chambers miles beneath the ground. Pressure builds as gases accumulate, trapped under heavy layers of rock that seal them in. Occasionally, the ground above swells by a few centimeters or small tremors shiver through the crust, but these changes unfold so slowly that they pass unnoticed by anyone living nearby. To human eyes, the land seems unchanging. To the earth, it is only the briefest pause between breaths. Supervolcanoes are rare beyond human memory, hidden deep in the rhythms of the planet itself. Their lives are measured in geologic time, not human generations. They awaken only when the balance beneath them tips, when molten rock and gas can no longer be contained. At that moment, the pressure beneath the crust tears through miles of stone, releasing energy with a violence that defies comprehension. Entire landscapes vanish within hours, ash clouds rise into the stratosphere, drifting across oceans. What begins as a local eruption becomes a planetary event, altering weather, dimming sunlight, and unsettling the delicate systems that sustain life. Because no one alive has witnessed a true supereruption, it is easy to mistake them for relics of a more dangerous past. The places where they sleep feel tranquil. People visit Yellowstone to watch geysers burst skyward in clouds of steam. Locals fish along the quiet shores of Lake Toba. From a distance, nothing about these places suggests catastrophe. Yet scientists who study them know that this calm is part of their nature. The magma beneath continues to shift and breathe, its heat warping the crust above in ways so subtle they can only be measured by satellites. Gas escapes through hot springs and fumaroles, carrying traces of carbon dioxide and sulfur that hint at the vast chamber below. These are not signs of immediate danger, but whispers from the deep earth, reminders that the power that shaped these places has never truly gone away. A supervolcano is more than a sleeping mountain. It is a reminder of the Earth's living heart, of the heat and pressure that build worlds and erase them. It hides beneath the quiet surfaces we take for granted, gathering strength in the stillness. To walk across such a landscape is to stand on the edge of something ancient and alive, a reminder that the ground beneath our feet is never as solid as it seems. In the heart of Sumatra, an island that stretches across the equator with mountains draped in mist and forests alive with the sound of cicadas, lies a lake that seems almost too vast to belong to one valley. Its waters are deep and blue, often calm enough to reflect the sky in quiet ripples. Villages gather along its edges, and ferries move steadily across its expanse, carrying people and goods, as if this were only a peaceful body of water, like so many others in the tropics. Yet beneath the surface of Lake Toba lies the mark of a catastrophe, a scar so large it can be seen from orbit. Lake Toba is not an ordinary lake. It is the remnant of one of the largest volcanic eruptions known in human prehistory. What appears today as a serene stretch of water, more than 100 kilometers long and about 30 kilometers wide, is in fact the collapsed roof of the Toba supervolcano. When the eruption occurred tens of thousands of years ago, so much material was ejected into the atmosphere that the land above the emptied magma chamber could no longer hold itself up. It caved inward, leaving a depression of staggering size. Over time, rain and rivers filled it, creating the lake that now seems so natural to those who live along its shores. To put its scale into perspective, Lake Toba is larger than the entire country of Singapore and roughly the size of Luxembourg. In many places it reaches depths of more than 500 meters. For anyone standing on its shore, it is difficult to see across to the far side without the horizon softening into haze. From the air, it looks more like an inland sea than a lake. Few would imagine that the water they are gazing upon rests inside a wound left behind by a blast that nearly ended the story of humankind. At the lake's center lies Samosir Island, itself larger than many modern cities. It was created when part of the land rebounded upward after the initial collapse. like a giant blister rising within the scar. The island now holds villages, rice fields, and winding roads that climb its slopes. Travelers who come to admire the scenery may walk among ancient stone monuments or rest beside traditional houses with sweeping roofs, never realizing they stand on ground lifted by forces that once shook the planet. The rocks around the caldera still carry the fingerprints of its violent birth. Along the lake's rim, cliffs of hardened volcanic ash and tuff reveal the story layer by layer. These deposits stretch outward for hundreds of kilometers, scattered across the Indonesian archipelago and beyond. Geologists studying them find crystals and minerals that formed in the intense heat of the eruption. The chemistry of these rocks tells of magma rich in silica, the kind that traps gases until the pressure builds to catastrophic release. Even today, hot springs bubble at certain points around the lake, releasing the smell of sulfur. These are quiet reminders that the magma chamber beneath Toba has not gone cold. The earth still breathes here, slowly, faintly, in ways that only instruments can measure. The ground around the lake sometimes swells or shifts over decades, and small earthquakes ripple through the region, subtle signs that the deep system is alive, even if resting. For the Batak people who have lived around Lake Toba for centuries, the lake is not only a landmark, but a source of legend. Myths describe it as a place born from the marriage of gods and mortals, its island rising as part of a great story of origins. Such myths preserve echoes of the awe that humans have always felt for this place, long after memory of the eruption itself vanished from human history. To scientists, Lake Toba is both a beautiful and sobering study site. Its sheer size is a reminder of what supervolcanoes are capable of. The caldera measures more than 100 kilometers at its longest point, making it one of the largest volcanic features on Earth. From its rim, visitors may see rolling hills and distant peaks, unaware that they are standing on the edge of an ancient crater so large that the human mind struggles to take in its full scale. The lake is tranquil now, a mirror for clouds and a gathering place for fishermen casting nets from wooden boats. Children play along the shoreline, and travelers photograph the sunsets that turn its waters gold. Yet the cliffs, the island, the mineral-laden springs, and the sheer expanse of the caldera all whisper the same truth. This is not a normal valley filled with rainwater. It is a scar left by a moment when the earth unleashed a power so immense that it reshaped the land forever. When Toba erupted, the earth did not simply tremble, it changed the sky itself. What began as a violent rupture deep within the crust became a process that reached the highest layers of the atmosphere, far above the reach of clouds and weather. Columns of ash and gas rose with astonishing speed, driven upward by heat so intense that the eruption's plume pierced into the stratosphere. This is the region of the sky where air grows thin, dry, and still, a place untouched by rain where whatever enters can linger for years. Once the ash and gases reached these heights, gravity could not easily pull them back down. Winds in the stratosphere began to spread them in broad, circling streams that encircled the planet. The eruption had become more than a local disaster. It had entered the machinery of the atmosphere itself. The Earth was wrapped in a drifting veil of fine particles, invisible to those who might have looked up, but powerful enough to change the balance between sunlight and shadow. Each fragment of ash was a microscopic piece of shattered rock and glass, jagged at the edges, born from the violent tearing apart of the mountain's interior. In smaller eruptions, ash might fall within weeks, settling on distant fields or washing away in rain, but in an eruption the size of Toba's, the sheer amount of debris overwhelmed the atmosphere. Billions of tons of fine ash rose high enough to avoid the cleansing reach of storms. Instead of falling, it spread outward, forming a haze that circled the earth. But ash was only part of the story. Along with it came immense quantities of gas, especially sulfur dioxide released from deep within the magma. Once it reached the stratosphere, this gas began a slow, quiet transformation. It met with water vapor already present at those altitudes and underwent a chemical reaction, forming tiny droplets of sulfuric acid. These droplets were so small that they behaved like smoke, hanging suspended for years. They did not block sunlight directly, instead they reflected and scattered it, sending much of it back into space before it could reach the ground. This delicate change in chemistry was enough to alter the planet's energy balance. Sunlight, which normally warms the oceans, soil, and air, was now filtered and weakened. The surface began to cool, first by fractions of a degree, then more sharply as the effect deepened. The cooling did not happen everywhere at once. Winds, ocean currents, and geography shaped its reach, but its influence spread steadily, changing the patterns of rain and the rhythm of the seasons. Scientists have seen modern echoes of this process. When Mount Pinatubo erupted in the Philippines in 1991, it sent nearly 20 million tons of sulfur dioxide into the stratosphere. The result was a measurable global cooling of about 0.5 degrees Celsius for nearly 2 years. Compared to Toba, Pinatubo was small. The scale of Toba's eruption was thousands of times greater, and models suggest that it could have reduced average global temperatures by more than 10 degrees. This was not a passing chill, it was a prolonged shift that lasted for years, perhaps even a decade, long enough to disturb ecosystems across continents. If you're enjoying this journey through Earth's most dramatic chapter so far, it would mean so much if you gave this video a like, and if you'd like to continue exploring these quiet mysteries with Simply About Earth, please consider subscribing. The ash and aerosols from Toba did not spread evenly. The stratosphere moves in bands with fast, stable winds near the equator. These currents carried Toba's emissions around the globe, looping them across Asia, Africa, and eventually toward the poles. Evidence of this journey lies in the geological record. Layers of volcanic glass, so thin they resemble dust, have been discovered across South Asia and even in East Africa. They mark the path of the cloud, proof that Toba's reach was not local but planetary. Once the sulfuric haze settled high above the world, the atmosphere itself changed character. Sunlight that did reach the ground was pale and diffuse, stripped of warmth. The air cooled rapidly at night, and the cycle of evaporation and rainfall faltered. Regions that had once been lush began to dry. Ice core samples from Greenland and Antarctica preserve the faint chemical signatures of this moment, layers rich in sulfur and trapped volcanic dust dating precisely to about 74,000 years ago. These frozen records reveal how deeply the eruption altered the air, confirming that sulfur aerosols had filled the stratosphere and persisted for years. To the eye, the change would not have been dramatic at first. The world did not go dark overnight, but each day a little less warmth reached the earth. The skies remained thinly veiled, the light colder, the air still. The planet had entered a new phase of its own making, a long, quiet twilight born from chemistry and ash, a fragile balance shifted by one eruption. Beneath this transformed sky, life would soon face the weight of that change. The eruption's true power was not only in the roar of the explosion, but in the invisible reactions that followed. High above the clouds, sunlight scattered, and the earth began to cool. Far away from the jungles of Sumatra, in the silent white deserts of Greenland and Antarctica, there are places where the earth keeps its memories in layers of ice. Snow falls year after year, compressing into ice sheets that are miles thick. Within these frozen layers are tiny bubbles of ancient air, crystals of ash and chemical traces that act like diary entries from the atmosphere. Scientists drill deep into the ice, pulling up long cylinders called cores. Each layer within these cores is a record of a season, a storm, or a shift in climate. When researchers examined ice dating back to 74,000 years ago, they found unmistakable signs of a sudden violent change. The layers showed a sharp drop in temperature, not a slow drift downward, but a plunge. Within just a few years, average global temperatures fell by more than 10 degrees. For comparison, the difference between today's climate and the height of an ice age is only about 5 degrees. That meant Toba's eruption cooled the Earth twice as much as the shift into an ice age. But it happened almost instantly. In the bubbles of air trapped in the ice, scientists also discovered higher concentrations of sulfur. The cooling was not even across the globe. Some regions grew colder, while others swung violently between wet and dry. In Africa, lake sediments tell of droughts that gripped vast regions. Cores drilled from the bottoms of lakes in East Africa show layers of clay and dust, where once there had been rich sediments from thriving plant and animal life. These sudden changes meant that rains failed, rivers shrank, and fertile plains withered into barren landscapes. What had been grasslands supporting herds of animals became empty stretches of dust. In Asia, the evidence is written in the soils and cave formations. Stalagmites in caves grow layer by layer from dripping water, and their chemistry reflects rainfall above ground. Around the time of the eruption, their growth slowed or stopped altogether. This tells scientists that monsoon patterns faltered, leaving once lush lands dry for years. In India, thick layers of volcanic ash are found in the soil, cutting across archaeological sites. Above these layers, the plant remains are different, showing that ecosystems collapsed and then slowly shifted into new forms. Forests struggled under the dim sky. With less sunlight, photosynthesis slowed, leaves grew sparse, and many trees died where they stood. Without vegetation to anchor the soil, erosion increased. Rivers carried silt and ash downstream, clogging deltas and wetlands. In colder regions, advancing ice and frost reshaped the land, locking water away in glaciers and leaving lower areas parched. The collapse of ecosystems rippled outward into the animal world. Large mammals that had relied on stable food sources were among the first to suffer. Herbivores found their grazing lands reduced, and as their numbers dwindled, the predators that depended on them also faced scarcity. Fossil records suggest that many species vanished from parts of Asia during this period, unable to adapt to the rapid changes in climate and vegetation. In Africa, animal populations contracted into smaller refuges where water and food remained. In the oceans, the impact was also recorded. Cooling of the atmosphere altered wind patterns, which in turn disrupted ocean currents. Sediment cores from the seafloor show shifts in plankton populations, the base of the marine food web. Cold-loving species expanded while warm water varieties declined. This upset the delicate balance of marine ecosystems, affecting fish and the animals that fed on them. The abruptness of these shifts is one of the most striking details. Normally, ecosystems evolve over centuries or millennia. Here, within only a handful of years, climates flipped and landscapes changed. For human groups scattered across the continents, these changes would have meant the sudden loss of familiar resources. Shelters of forests disappeared, game animals vanished, and water became unreliable. Survival required adaptability on a scale that had never been demanded before. Scientists pieced together these stories from many different sources. The frozen record of the poles, the mud at the bottom of lakes, the growth rings of cave formations, the chemistry of ancient soils, and the fossils of plants and animals that lived and died in those years. Each fragment points to the same truth, that the eruption of Toba did not only darken the skies, it disrupted the very systems that life depended on. The world froze, the rains faltered, and ecosystems on every continent were reshaped. For years, perhaps decades, the Earth moved under a new rhythm, one born from fire that turned quickly into cold. When the world cooled after Toba's eruption, survival itself became uncertain. The skies above remained pale and weak, and the air grew colder with each passing season. Across vast stretches of land, plants withered where they stood, forests fell silent, as animals disappeared, leaving only the sound of wind moving through the ash. For the first time in our species' history, it seemed that the Earth had turned against life. At that time, humanity was not a sprawling civilization, but a scattered species. Our ancestors lived in small, mobile groups, bound by family, language, and the shared knowledge of how to find food and water. They followed the rhythms of nature, hunting, gathering, and moving with the seasons. But in the years after Toba erupted, those rhythms shattered. The familiar patterns of rain and sunlight broke down. Places that once fed them grew barren. Rivers and coastlines shifted. The balance that had sustained early humans was suddenly gone. In this harsh new world, every day was a test of endurance. Nights grew longer and colder. Fires were harder to keep burning as wood became scarce. Game animals vanished from the open plains, migrating or dying as vegetation failed. Even the smallest mistakes could mean death for an entire group. Many must have perished quietly, their stories lost in the silence that followed. Scientists studying this period call it a population bottleneck, a moment when the human population may have shrunk to a tiny fraction of what it once was. The term describes more than just loss of life. It marks a narrowing of existence, when an entire species is pressed to the brink, and only a few survive to carry the story forward. For humans, this bottleneck was not caused by war or disease, but by the planet itself reacting to a single eruption that changed the climate of the world. The scale of that contraction is difficult to imagine. Some estimates suggest that the number of humans on Earth may have fallen to only a few thousand breeding individuals. Entire branches of families could have vanished, leaving behind no descendants. Whole regions may have been emptied of people. On a global scale, the species came dangerously close to disappearing entirely. There were no cities then, no nations to record the struggle. What happened took place quietly over generations, hidden in the cold wind and ash. A few groups survived in pockets where the environment remained stable enough to support life, along coastlines. Some may have gathered food from the sea, turning to shellfish and marine plants when hunting failed. In Africa, where the climate may have been slightly more forgiving, small populations found refuge near lakes and rivers. Their numbers were small, but they endured long enough for the world to begin healing. For these survivors, life was fragile but continuous. They had no knowledge of how close they stood to extinction. What they understood was the landscape before them, the immediate need to find warmth, food, and safety. Every hunt, every spark of fire, every newborn child was an act of defiance against a world still shadowed by ash. The bottleneck did not last forever. As the atmosphere slowly cleared and sunlight returned to full strength, vegetation began to recover. Animal populations followed, and with them human groups expanded once again. But that period of near annihilation left a permanent mark on the story of our species. It was a moment when the future could have gone either way, when a few isolated bands of humans determined whether the line would continue or end. This event reminds us that humanity has never been immune to the forces of nature. Our ancestors were not conquerors of their world, but survivors within it. They lived at the mercy of storms, droughts, and cold, yet managed to endure through cooperation and persistence. The world they inhabited was vast and empty, and for a time they were almost alone upon it. The memory of that near extinction lives not in written words, but in the very fact that we exist. Each person alive today is a continuation of those few who made it through the long winter that followed Toba's fury. Entire generations passed without knowing whether warmth or stability would ever return. And yet somewhere, along windswept shores and silent plains, small fires continued to burn, carrying the last threads of human life through one of the darkest chapters the earth has ever written. Every person alive today carries a record of ancient survival. It is not written in journals or carved into cave walls. It lives quietly inside the body, hidden in the coiled strands of DNA. Within those spirals are traces of everything our species has endured: droughts, migrations, and the long cold years that followed Toba's eruption. These molecular patterns are not stories told through words, but through absence, scarcity, and the quiet fingerprints of survival left in our genetic code. DNA is made of long sequences of chemical bases that form a kind of living memory. When scientists read this code, they find a striking truth. Despite the billions of people alive today, humans are far less genetically diverse than many other animals. Chimpanzees, which number only in the hundreds of thousands, show greater genetic variation than we do as a species spread across an entire planet. This unexpected uniformity is one of the strongest pieces of evidence that humanity once passed through a severe population bottleneck, a time when our numbers fell so low that most of our genetic diversity was lost. In the simplest sense, a bottleneck is a narrowing of life. Imagine a vast river of human ancestry suddenly forced through a narrow channel. Only a few genetic branches survive that passage, and everything that comes after carries the mark of that restriction. Scientists can see this in our DNA today. Across the genome, there are regions where variation should exist but does not. Instead of many different versions of genes, the usual signature of a large, healthy population, there are long, uniform stretches repeated almost identically from person to person. These are the genetic scars of near extinction. Each missing variation tells part of the story. When populations shrink suddenly, random chance begins to shape evolution more than natural selection. Many lines of inheritance vanish simply because the people carrying them do not survive. Over generations, the surviving group's genetic patterns become dominant by default, even if they represent only a fraction of the diversity that once existed. That is what scientists see when they study modern human DNA, a record of survival written through loss. The timing of this genetic contraction matches what geological and archaeological evidence suggests about the aftermath of the Toba eruption around 74,000 years ago. Volcanic ash covered much of southern Asia, and the global climate cooled sharply. As the skies dimmed and food sources dwindled, the human population likely plummeted to a few thousand breeding individuals. The genetic evidence fits this scenario almost too perfectly. It shows that humanity's diversity collapsed around that same window in time, as if the planet itself had pressed reset on the species. These signatures are not limited to one region or population. When researchers compare DNA samples from across the globe, they find that all people from Africa to the Arctic share remarkably similar genetic markers. This global similarity suggests that every modern human descends from a small, isolated group that survived through those years of environmental collapse. The tiny pool of genes that passed through that narrow gate became the foundation for all human life that followed. Mitochondrial DNA, which is inherited only through the maternal line, offers one of the clearest signals of this ancient narrowing. In large populations, mutations accumulate at a steady pace, creating many branches on the family tree. But in humans, mitochondrial variation is surprisingly limited, as if only a handful of maternal lines survive to rebuild the species after the bottleneck. The same pattern appears in the Y chromosome passed from fathers to sons. Both reveal a shared story, the genetic record of a population that once hovered on the edge of disappearance. For scientists, reading these signals is like tracing the echoes of a whisper across deep time. Each shared sequence is proof of endurance, a silent record of ancestors who lived through famine, cold, and scarcity. Their DNA carries the imprint of stress, of hardship survived at immense cost, and because every living human descends from that small population, those ancient signatures exist within all of us, quiet reminders of how close the species once came to vanishing. It is humbling to realize that our genetic sameness is not a sign of weakness, but of survival. It is the residue of a moment when life contracted to its smallest spark, then began to grow again. In those years after Toba, every birth was a continuation of something fragile and extraordinary. The earth was cold, the skies dim, but life, against all odds, continued. And the evidence of that endurance still travels through time, encoded in the chemistry of every cell, carrying the faint, enduring memory of humanity's narrow escape. When the skies dimmed, and the earth cooled after the eruption of Toba, life for our ancestors became a struggle measured one day at a time. Across vast regions, plants withered, animals disappeared, and once familiar landscapes turned into places of silence. Yet somehow, small groups of humans managed to hold on. Their survival was not guaranteed by strength alone, but by resourcefulness, memory, and the bonds they formed with one another. In many places, food that once came from forests or grasslands became unreliable, with plants failing to grow under the darkened sky and grazing animals vanishing in search of food or dying in great numbers. Humans had to look elsewhere. Along the coastlines of Africa and Asia, the sea offered what the land could no longer provide. Shellfish, crabs, and seaweed became lifelines. Unlike plants that depended on sunlight or animals that required wide pastures, the creatures of the tide were more resilient to sudden changes in climate. Shellfish could still be gathered in abundance from rocky shores, and fish continued to swim in the shallows. Evidence from ancient sites along the southern tip of Africa shows that humans turned to these resources, leaving behind heaps of shells that speak to meals taken in desperate but determined times. The act of foraging along the sea was more than a way to eat. It required timing and skill, knowing when the tides would reveal mussel beds, or when waves would retreat enough to expose crabs hidden in the sand. It also demanded knowledge of which plants of the shore were edible and which might sicken the body. These skills were learned and shared, passed from one generation to the next, carried in memory like a kind of map. In this way, survival was not only physical but cultural. The knowledge of where to look and how to gather became as essential as the food itself. Inland survival was far more uncertain, yet even there people found refuges. In Africa, some groups are thought to have taken shelter along rivers and lakes, places where water was more stable and small pockets of vegetation survived even in harsher conditions. In Asia, archaeological sites in India suggest that humans persisted despite thick layers of ash blanketing the land. Stone tools found above and below the ash layers show that communities adapted, continuing their traditions even as their world shifted around them. These sites reveal not a complete break, but resilience, as if people bent but did not break under the weight of the eruption's aftermath. What kept these scattered groups alive was not only their environment, but also their capacity to work together. In small bands, every individual mattered. Children were carried and protected, elders were sources of memory and guidance, and hunters shared what little could be found. When food was scarce, sharing became more than kindness. It was the only way to keep a group from falling apart. Cooperation meant that even when one family had little, another could provide enough for all to endure another day. This kind of support formed a web of survival, fragile yet strong enough to hold under enormous strain. Memory also played a quiet role, the ability to remember where food had once been found, which plants sprouted first after a drought, or which animals could still be trapped when larger prey vanished, gave groups an advantage. These memories became stories told by firesides, instructions given to children and traditions carried forward. In this way, information about survival became part of the fabric of culture, binding people together through shared experience and knowledge. Adaptability was the final thread that kept humanity from slipping away. Our ancestors could not control the skies or the cold, but they could shift their habits. They turned from hunting large animals to gathering shellfish. They experimented with new plants, crafted different tools, and learned to survive in landscapes that no longer looked the same. Each change was small, but together these adjustments formed a pattern of endurance. Archaeological traces from this time show hints of innovation. Tools became more refined, suited for gathering different resources. Fire was used not only for warmth, but also to cook shellfish, making them easier to digest. Shelters were built from whatever could be found, protecting families against winds that carried ash and cold. These details suggest that humans did not simply endure passively, they adapted actively, shaping their behavior to meet the demands of an altered world. For those who lived through it, survival was likely a quiet and constant effort. Each day required choices: where to move, what to eat, how to share, and when to rest. Each choice built upon the one before, creating fragile chains of life that reached through the long winters of ash. What remained after those years were not large, thriving populations, but small, scattered groups who had endured through a combination of resourcefulness and cooperation. Their lives left few traces on the earth, but the fact that any trace exists at all is proof that they succeeded. When the great eruption of Toba unfolded, its reach extended far beyond the human story. It swept through the animal kingdom with silent precision, rewriting the patterns of life that had shaped the continents for ages. Before the ash began to fall, the lands of Asia and Africa teemed with immense creatures, herds of giants that grazed, hunted, and migrated in endless cycles. The plains and valleys of the Pleistocene world were alive with movement. Elephants taller than modern ones, rhinoceroses with armor-thick hides, giant deer with antlers that could stretch wider than a man's height, and predators large enough to bring them down. In the world before Toba, abundance was the rule. Afterward, it became the exception. The term megafauna is used to describe these large animals, and many of them vanished in the years that followed the eruption. Fossil records from India and Southeast Asia show abrupt breaks in the presence of large mammals soon after the layer of Toba's ash was laid down. The changes were sudden, recorded in the bones and teeth buried beneath the earth. Where once there had been dense herds of grazers, there were gaps, long silent periods in the fossil record where no large herbivores are found. Those that perished first were often the most specialized animals that depended on particular diets or climates, had no defense against the sudden change that followed the eruption. Giant deer that had thrived on wide grassy plains could not adjust when their food sources dwindled. Ancient species of elephants and cattle which required massive quantities of vegetation to survive found the world too barren to sustain them. Even top predators such as saber-toothed cats and large hyenas fell into decline when their prey disappeared. The losses rippled upward through the food web. For every species that vanished, several others that depended on it were pushed closer to the edge. Fossils from this time show not only the disappearance of individual species, but also a collapse in diversity across entire groups of animals. The great tapestry of life that had seemed so stable began to unravel thread by thread. Yet even as the giants fell, smaller, heartier creatures began to take their place. Evolution favors flexibility in times of crisis, and in the quiet years that followed the eruption, adaptability became the currency of survival. Rodents, with their quick breeding cycles and simple diets, began to thrive. They could burrow into the ground for warmth and feed on roots and seeds when surface vegetation failed. Small carnivores, such as foxes and civets, survived by scavenging whatever remained. Wild boars, ever resourceful, used their keen sense of smell to dig up tubers and insects. Birds, too, endured. Species that fed on insects, grains, or carrion proved remarkably resilient. Some migrated to safer regions while others remained and adapted to the changed conditions. In many areas, their presence helped keep ecosystems alive, dispersing seeds and controlling insect populations when larger animals could not. Even among the reptiles and amphibians, endurance found its champions, tortoises and crocodiles, whose lives moved at the slow rhythm of ancient time, continued largely unchanged. Their cold-blooded metabolism and simple diets made them well-suited for survival in a cooling world. While the forests and plains emptied of giants, the rivers and wetlands still rippled with life that carried on, quiet and steady. In the centuries that followed, as the air cleared and the earth began to warm again, the survivors spread into the spaces left vacant by extinction. Small mammals multiplied rapidly, taking advantage of the absence of competition. Some species evolved into new forms entirely, giving rise to the ancestors of many animals we know today. The disappearance of the giants created opportunities for the small and nimble, for those that could adapt to scarcity rather than depend on abundance. This shift in the balance of life was one of the great turning points in natural history. It marked the moment when the world of enormous beasts gave way to one dominated by smaller, faster, and more adaptable forms. Humanity, too, was part of this new order. The people who endured alongside these changes found themselves hunting smaller prey, watching new creatures emerge where familiar ones had gone. The rhythms of the animal world were changing, and humanity was changing with them. Toba's eruption had thinned the ranks of life, but it had not erased it. In the ashes left behind, the story of survival continued, not in the thunder of heavy feet, but in the rustle of small ones. The creatures that endured were not the most powerful or the most fierce. They were the ones that could bend, shift, and find life in the cracks of a broken world. From their endurance, the planet began slowly to breathe again. When Toba erupted, its power did not stay confined to Sumatra. What began as a violent wound in the earth quickly became a global event, its reach stretching across oceans and continents. Ash carried high into the stratosphere began to drift on winds that circled the world. Tiny fragments of pulverized rock and glass, sharp as blades under a microscope, fell in places far removed from the mountain that had birthed them. The eruption was not simply a local disaster, it left its fingerprints in lands thousands of kilometers away, an invisible veil settling across the skin of the earth. In India, thousands of kilometers northwest of Sumatra, geologists have uncovered thick layers of volcanic ash, sometimes several meters deep. These deposits are unmistakable in their composition. The grains are light grey to pale white, rich in volcanic glass, and contain minerals that match the chemistry of Toba. When archaeologists dig into ancient soils and find these ash layers, they discover abrupt interruptions in the story of the land. Below the ash lie traces of life as it had been, with stone tools and plant remains. Above it, the evidence shifts, altered by the sudden fallout that smothered the ground. The spread went far beyond South Asia, across the Arabian Peninsula, and into East Africa. Scientists have found thinner, but still distinct layers of Toba's ash, carried by high-altitude winds. These fine particles traveled immense distances before settling on the ground. In some places, the layer is so thin it can be mistaken for ordinary dust, but chemical analysis reveals its true origin: tiny shards of volcanic glass preserved for 74,000 years, confirming that the ash that began in Sumatra fell on soils half a world away. Even in Africa's Great Rift Valley, where some of humanity's earliest ancestors once walked, traces of Toba's eruption can be found. Sediments from ancient lakes preserve faint layers of ash that arrived long after the eruption itself, sifted down from the sky like a slow snowfall. To imagine standing there at the time is to picture a quiet rain of pale dust falling across savannas and hills, settling on grasses and watering holes, leaving behind a faint grey blanket that stretched as far as the eye could see. The ash did not fall evenly. The coarser, heavier fragments settled closer to the source, blanketing Sumatra and surrounding islands in thick deposits. In these areas, the land would have been buried under meters of choking dust, forests smothered and rivers clogged. Farther afield, the particles became finer, carried like smoke through the atmosphere. These tiny shards could remain suspended for weeks or months before finally drifting down, covering distant lands in layers no thicker than a sheet of paper. Yet even thin layers were enough to alter the soil, affect water supplies, and mark the geological record. The cloud spread was so vast that it became a global marker, a line in the Earth's history that scientists can trace across continents. In core samples drilled from lakes, peat bogs, and ocean floors, this layer of ash serves as a timestamp. Wherever it is found, scientists know they are looking at sediments from the same moment, 74,000 years ago when the world was touched by Toba. It is a kind of signature written in dust, binding together distant lands in a single shared event. In some regions, the ash still lies undisturbed beneath the surface, a pale line separating older soils from newer ones. Farmers may never notice it as they plough fields or dig wells, but beneath their feet lies the quiet memory of a volcanic winter. In caves, too, ash particles can be seen trapped within stalagmites, carried by dripping water and locked in stone over the millennia. If you've been finding this journey through Earth's deepest mysteries as fascinating as I hope, please consider subscribing to Simply About Earth. Your support helps us continue exploring these stories that connect us all to the planet's incredible history. Even the deepest parts of the oceans were not beyond its reach. Sediment cores from the Indian Ocean reveal ash particles buried under layers of silt, still sharp and unweathered after tens of thousands of years. The sheer scale of this distribution reminds us of how far a single eruption can reach. What began on a mountain in Sumatra became a planetary event, scattering dust across half the globe. The physical spread of Toba's ash was not just an atmospheric veil that dimmed the skies, but a tangible rain of particles that left its mark on the land itself. From India to Africa, from rivers to deserts to ocean floors, The Earth still holds these traces, quiet reminders of the day the world was blanketed in dust. When the roar of Toba's eruption faded and the clouds of ash had already risen into the heavens, what followed was not silence as we know it. It was a different kind of stillness, heavy and unsettling as if the very breath of the planet had been stolen away. The world beneath the drifting plume was no longer governed by the familiar rhythms of wind and rain. The eruption had not only darkened the skies, it had rewritten the rules of the atmosphere itself. At first, the changes were subtle. The winds that once swept steadily across continents began to falter. The great rivers of air high above the surface, the jet streams that shape weather and guide storms, lost their usual paths. They bent and shifted unpredictably, tugged by temperature contrasts that had never existed before. Layers of fine ash and droplets of sulfuric acid in the stratosphere scattered sunlight back into space, cooling the air unevenly from pole to pole. Places that had once felt the steady passage of seasons began to slip out of sync with the calendar. Summers were late or never came at all. Winters clung to the land far past their time. The cooling was not gentle. As the upper atmosphere reflected sunlight away, the surface of the earth responded in kind. Oceans that had once absorbed vast amounts of heat began to lose their warmth. As surface waters cooled, evaporation slowed. Clouds formed differently, less predictably. As the balance between air and sea was disturbed, rainfall patterns that had remained stable for thousands of years broke apart. In some regions, rain stopped almost entirely, leaving the ground cracked and dry. In others, storms gathered with unusual ferocity, their energy shaped by shifting currents of cold and heat. The familiar monsoon belts that had sustained life in tropical regions weakened or disappeared, leaving once green landscapes parched and barren. Even the great circulations of air that connected the hemispheres were thrown into confusion. Trade winds slackened, polar fronts pushed farther south, air masses stalled over some regions, creating droughts that lasted far longer than any living thing had known. In other places, rain fell relentlessly, flooding valleys that had never seen such water before. The weather became a tapestry without pattern, its threads pulled apart by the imbalance in the sky. The cryosphere too began to change. As the planet cooled, snow lingered longer into spring. Glaciers crept forward from the mountains, reclaiming ground they had not touched in centuries. Sea ice stretched farther from the poles, forming barriers that altered ocean currents and deepened the global chill. The cooling fed itself, creating a feedback loop that locked the world into a colder, harsher climate. It was a transformation that touched every corner of the Earth, from tropical forests to polar seas. The disruption did not remain confined to the atmosphere alone. With the jet streams shifted and the hydrological cycle fractured, the timing of life itself began to falter. Plants that relied on certain temperatures or rainfall to bloom failed to flower. Rivers that once flooded predictably to nourish floodplains now surged unpredictably or dried up without warning. Migration routes of birds and animals, shaped by thousands of years of stable seasons, no longer led to food or water. The natural clock that governed Earth's living systems had been broken, and with it the web of relationships that life depended on. Years passed, and still the air carried the memory of that moment. The tiny droplets of sulfur and fine volcanic ash that hung suspended in the stratosphere did not fall quickly. They circled the globe, caught in winds that rarely touched the surface, scattering sunlight back into space month after month. Seasons blurred. Generations of plants and animals lived and died under skies that never returned to their former clarity. Even as the first signs of recovery appeared, the climate did not return to what it had been. The Earth had shifted to a new equilibrium, colder and more unstable than before. It would take decades for the atmosphere to fully cleanse itself, for rains to wash the last traces of aerosols from the sky, and for winds to regain their old strength. By the time they did, the world was a changed place. Landscapes had transformed, ecosystems had reassembled themselves in unfamiliar patterns, and the memory of a stable climate had become just that, a memory. And yet, Even as the skies began slowly to clear, they carried the imprint of what had happened. The air itself had become a witness to catastrophe, altered in ways that would leave their mark for generations. And when sunlight finally filtered through the thinning haze, it did so with a strange, haunting quality, a signal that the next chapter of this story was about to begin. After the eruption of Toba, the world's skies changed in ways that would have unsettled even the strongest among our ancestors. The ash and sulfur drifting high above the earth altered the very light that reached the ground. Sunrises and sunsets, once gentle transitions of gold and blue, became strange and otherworldly. Twilight glowed with deep reds and metallic coppers, as though the heavens themselves were burning. For people who had never seen such sights, the daily rhythm of light must have felt both mesmerizing and ominous, each evening and morning painting the world with reminders of the disaster that still lingered above them. The cause of these skies lay in the particles spread through the stratosphere, volcanic ash, sulfuric droplets, and fragments of glass scattered sunlight in unusual ways. Instead of clear beams passing cleanly through the air, the light was bent, filtered, and broken. Shorter wavelengths of light, like blues and greens, were scattered out, leaving behind the dominance of reds and oranges. The effect stretched across continents, uniting distant lands under skies that seemed aflame. Even in regions where the ash layer on the ground was thin, the heavens betrayed the scale of the eruption. In later times, long after Toba, written records describe similar transformations of the sky after other great eruptions. When Mount Tambora erupted in the year 1815, its plume filled the atmosphere with ash and sulfur. The following year became known as the year without a summer. Across Europe and North America, sunsets glowed with eerie brilliance. Painters captured skies streaked with strange hues, blending crimson, violet, and copper into scenes that seemed unreal. Crops failed under the cold that followed, but the skies themselves remained unforgettable, haunting witnesses with their surreal beauty. Another example came after Krakatoa erupted in 1883. The blast was heard thousands of kilometers away, but its more lasting mark was in the skies. Observers described sunsets that burned with unnatural intensity, colors so vivid they seemed like fire stretched across the horizon. For months, reports came of skies turning scarlet even long after dusk, the light bending through high layers of dust. Some believed the world was ending. Unable to explain such spectacles in familiar terms, scientists later realized that the volcanic particles in the stratosphere had created a global filter, much like what Toba must have unleashed on a far larger scale. These later records offer glimpses into what people 74,000 years ago may have seen. Without writing, their impressions could not be preserved in words, but the memory may have been carried in stories, myths, and oral traditions passed down over generations. Tales of fiery skies, of endless twilight, or of red-stained heavens may find their roots in the altered light of volcanic winters. The haunting glow of sunsets would have been a daily reminder that the air itself had changed. The beauty of such skies was both magnificent and poisonous. The same particles that painted the heavens in copper and red also blocked sunlight from reaching the Earth's surface. They chilled the planet, shortened growing seasons, and weakened ecosystems. What seemed beautiful to the eye carried within it the seeds of famine and collapse. The copper twilight was the surface of a deeper shadow, a sign that the world below was struggling to breathe and grow. Scientists studying ice cores and sediments can measure the chemical traces of these events, but they also know that light itself carried part of the story. Accounts from the year without a summer describe people marveling at skies they had never seen before. Similar astonishment would have been felt by those living in the aftermath of Toba, who watched familiar cycles of day and night reshaped into something uncanny. Dawn no longer brought gentle warmth, and dusk no longer faded quietly into night. Both became stages for displays that blended beauty and threat in equal measure. For years after Toba, the atmosphere remained altered, the haze of ash and aerosol slowly drifting but never fully gone. Each morning and evening, the survivors of that age would have looked upward at skies painted in strange colors. Those colors may have seemed like fire burning just beyond reach, reminding them of the mountain that had changed their world. The story of Toba's eruption and the mystery within our DNA has long fascinated scientists. The evidence is clear that at some point in our distant past, humanity's genetic diversity narrowed sharply. Yet the cause of that narrowing remains one of the great debates in evolutionary science. Was the super-eruption of Toba the primary reason, plunging the planet into a volcanic winter so severe that only a few thousand humans survived? Or was the story far more complicated, shaped by a web of overlapping challenges that unfolded over thousands of years? For many researchers, the Toba hypothesis once seemed the perfect fit. The eruption was extraordinary in scale, among the largest in the last 2 million years. More than 2,000 cubic kilometers of ash and gas were blasted into the atmosphere, forming a veil of sulfur aerosols that dimmed the sun and cooled the planet. Climate models show that global temperatures may have dropped by more than 10 degrees, triggering years of failing crops, collapsing ecosystems, and food scarcity. It was easy to imagine small, scattered populations of early humans being pushed to the edge by such an event. The genetic data showing a steep drop in human diversity appeared to echo that same story of near extinction. But as genetic tools have grown more precise, scientists have begun to question whether Toba alone could explain the patterns written in our DNA. The evidence of a bottleneck is real, but the fingerprints of its cause are more blurred than first believed. DNA does not record the why of an event, only the effect, and many forces, environmental, biological, and social, can produce the same genetic signature. Some researchers point to disease as a possible contributor, even long before the rise of agriculture and dense human settlements. Pathogens likely moved through early populations. A new infection spreading among small hunter-gatherer groups could have wiped out many individuals while sparing those with natural resistance. Such selective survival would leave behind a narrower genetic pool, just as a volcanic catastrophe might. The idea that microbes could reshape the destiny of our species adds another layer to the puzzle, one that does not require fire or ash to explain the loss of diversity. Migration is another thread in the debate. As early humans began their slow dispersal out of Africa, they did not travel in great numbers. Small bands moved across harsh and unfamiliar lands, often separated by thousands of kilometers of desert, mountains, and sea. Along the way, accidents, hunger, and conflict would have taken their toll. Each wave of migrants carried only a fraction of the total genetic variation of their ancestors, leaving behind others who perished or remained isolated. Over time, this process, known as the founder effect, can mimic the genetic pattern of a bottleneck even without a sudden global disaster. Climate itself, even apart from volcanic activity, may also have played a part during the Pleistocene epoch. Earth's climate swung between periods of intense glaciation and relative warmth. Lake sediments in Africa record abrupt droughts and recoveries, showing how entire regions could turn from fertile to barren in a matter of generations. These shifts would have fragmented populations, forcing them to cluster near shrinking water sources or migrate in search of new ones. Each episode of stress would have trimmed the population further, and over thousands of years the result could have looked much like a single catastrophic collapse. Because of these competing explanations, the Toba hypothesis has become less a conclusion and more a starting point for discussion. Some scientists argue that the bottleneck might not have been as sharp or short-lived as once thought. Instead of one devastating blow, humanity may have endured a long series of pressures that gradually eroded its genetic diversity. In this view, Toba's eruption was only one chapter in a longer story, an especially dark and dramatic one, but not the sole author of our near extinction. Still, the case for Toba remains compelling. The geological evidence aligns closely with the genetic timeline. Ice cores from Greenland and Antarctica show clear spikes of sulfur around 74,000 years ago. Precisely when the eruption occurred, layers of ash found across India and the Indian Ocean match the same date. Archaeological sites show sudden breaks in continuity, abandoned tools, vanished species, and disrupted habitats that all hint at a world briefly pushed beyond its limits. Perhaps the truth lies between extremes. The eruption of Toba may have delivered a catastrophic shock that magnified other stresses already in motion. Populations weakened by climate instability or disease might have found themselves unable to recover after the volcanic winter. The bottleneck, then, was not the product of one event, but the culmination of many. What scientists agree on is that this period reshaped the course of human history, whether by ash, ice, or illness. Our ancestors faced a convergence of forces that tested the species' endurance. The debate continues, not because the evidence is uncertain, but because it reminds us how fragile life can be and how many paths lead towards survival or extinction. Beneath the soil of India, hidden in riverbeds and ancient terraces, lies a quiet record of survival. Archaeologists digging through the layers have uncovered simple stone tools shaped and sharpened by human hands tens of thousands of years ago. They are small things, not much to look at, often just flakes of rock carefully chipped into cutting edges. Yet their placement in the earth tells a story. Some lie beneath a layer of pale volcanic ash, while others rest above it. The ash belongs to Toba, the blanket it spread across the land 74,000 years ago. The tools beneath were made before the eruption, and the tools above were made after. Side by side, they whisper a message: humanity did not vanish. The sites in India are striking because the ash layer is often thick and unmistakable. In some places it can be traced for hundreds of miles. It is the same ash that once darkened skies across the globe, and here it acts as a divider in the soil, marking a before and an after. When researchers sift through these layers, they see that the style of the stone tools hardly changes across the divide. The same techniques, the same flaking patterns appear on tools both under and over the ash. This continuity suggests that the people who lived there endured the eruption's aftermath. They may have faced hunger, darkness, and poisoned landscapes, but they adapted, found food, and kept shaping the stones that had always been their lifeline. These findings are important because they challenge the idea that humanity nearly disappeared everywhere. While genetic studies suggest a bottleneck, with numbers reduced to perhaps only a few thousand, archaeology reminds us that survival was uneven. In some regions, groups may have perished, leaving no descendants. In others, small communities clung to existence, their presence written not in fossils or bones, but in the quiet persistence of tools. Africa tells a similar story. Excavations across the continent have revealed stone tools scattered through the same broad time frame. In the Rift Valley, in caves along the southern coast, and in the open savannas, tools appear both before and after the period of global cooling. These tools, like those in India, show continuity. The people who crafted them lived through the hardest winters, perhaps sheltered in coastal refuges, where shellfish and seaweed offered a steady source of food. Some researchers believe these African populations may have been crucial to humanity's survival, while others struggled inland. Those near the sea could depend on resources that were less affected by the cold and drought. Their stone tools, found in abundance, are the evidence left behind. What makes these discoveries powerful is not the tools themselves, but their ordinariness. They are not masterpieces of craftsmanship, not ornate or decorated. They are functional, often crude, yet they represent knowledge passed down through countless generations. To shape stone into something sharp takes skill, practice, and memory. The fact that this knowledge continued after the ash fell means it was never lost. Somewhere, parents taught children to strike flakes from a core, to sharpen an edge against bone or wood. Even in the bleakest conditions, traditions held. In some Indian sites, archaeologists found tools buried directly in the ash. Imagine the scene: people moving across a land where grey dust blanketed the ground, still leaving behind signs of work. Perhaps they used stones to cut plants struggling through the dust, or to carve the remains of animals that had fallen in the chaos. The tools are not just artifacts. They are traces of human breath and motion, evidence that life continued even when the world seemed broken. Stone tools are also resilient in a way that bones and shelters are not. They do not rot, they do not burn away, and they do not crumble with ease. Because of this, they outlast everything else. The people who made them may have left no graves, no written words, no walls of houses to study, but the stones remain, durable markers of human persistence. Their very durability gives us glimpses of moments that would otherwise be forgotten. The tools found in these sites also tell us something about adaptation. Archaeologists noticed that in some regions, toolkits became simpler after the eruption. This may have reflected smaller groups with fewer resources, relying on the quickest methods to make what they needed. In other areas, tools became more diverse, as if experimentation flourished under pressure. Both patterns reveal how humans responded differently to the same disaster. Some streamlined, others innovated. Survival could take many forms. When scientists kneel in the dust of India or Africa and brush away soil to reveal a stone flake, they are not just finding rock. They are uncovering evidence of breath held, of hands working, of persistence across impossible odds. Each tool marks a pulse of life that did not stop beating, even when the earth shook and the skies went dark. When the fury of the eruption faded, the silence that followed was strange and heavy. It was not the calm of recovery, but the quiet of absence, a planet that had exhaled too much and was left breathless. Across continents, the living fabric of the earth began to unravel. Forests, grasslands, and rivers that had once pulsed with life now lay cloaked in a grey stillness. The forests were among the first to fall. Trees that had stretched toward the sky for centuries were smothered in ash, their leaves curling into brittle husks. Layers of fine volcanic dust covered every branch and leaf until the green was gone. Without sunlight, photosynthesis slowed, and the great engines of the biosphere began to stall. The air itself grew heavy with the scent of decay, the breath of a world whose lungs were clogged. When the rains came, they mixed with the ash and formed acid-laced mud that stripped bark from trunks and leached nutrients from the soil. What had been vibrant ecosystems collapsed into ghostly groves of standing wood, skeletal and silent. The grasslands fared little better. The fine ash settled thickly over the open plains, sealing the ground beneath a grey crust. Seeds waiting in the soil for the return of rain were buried too deeply to sprout. The once endless carpets of green became flat expanses of dust that stretched to the horizon. The rhythm of life that had pulsed through these plains, the cycle of growth, grazing, and regrowth, broke apart. The sounds that had once filled the air, the whisper of wind in tall grass, and the soft thud of hooves, faded into the background of the planet's hush. Rivers that had once given life to these landscapes turned against them. Streams running from the mountains carried thick torrents of ash downstream. Waters that had been clear grew opaque and heavy, their surfaces rippling with the oily sheen of sulfur. Ash settled on the riverbeds, burying aquatic plants and smothering the small creatures that depended on them. Each rainfall washed more debris into the flow, spreading the poison farther. Some rivers vanished entirely as the volcanic dust absorbed rainfall before it could collect into channels, turning once fertile valleys into stretches of cracked mud. In the lakes and wetlands, oxygen fell to nothing. Ash sealed their surfaces like a lid, and without light, algae could not grow. The still waters turned stagnant, dense with rotting plant matter. Sediments preserved these moments like photographs, layers of grey recording the exact time when life faltered. Modern scientists have found those layers in places far from Indonesia, across India, Africa, and even the Middle East, all telling the same story of suffocation and stillness. Even the oceans felt the weight of the catastrophe. Winds carried sulfur and ash across vast distances, where it rained into the sea and altered its chemistry. The cooling air above chilled the surface waters, disturbing the delicate balance that sustained plankton blooms. Without plankton, the ocean's food chains weakened from the bottom up. Though the depths remained a refuge, the upper layers that once glittered with light became dim and sparse. On land, the absence of plants reshaped everything. without roots to hold soil in place. Erosion scoured the ground, hillsides crumbled into valleys, and valleys filled with drifting ash. Dust storms became a new and constant presence, sweeping fine particles across entire regions. The sun, already dimmed by haze, struggled to pierce the shifting veil of dust that danced between earth and sky. Time passed, and still the wounds deepened. In tropical regions, heavy rains eventually began to wash the ash away, but they also carved new scars into the land. Rivers changed their courses, cutting fresh paths through the altered terrain. In colder areas, winter snow preserved the fallout, sealing it beneath white blankets that would later freeze into the ice sheets we study today. Those dark layers inside Greenland's ice cores mark the instant when the planet seemed to pause, caught in the aftermath of Toba's eruption. Recovery was neither quick nor certain. The first signs of renewal came from the smallest of plants, mosses and hardy weeds that rooted in the cracks of the ash. Their presence was subtle, green specks appearing against the grey. Over years and then centuries, they helped rebuild the soil, drawing back insects, fungi, and the early pioneers of returning forests. The process was patient, stretching beyond the memory of any creature that had lived through the disaster. Earth itself endured as it always has, but for a time it was quieter. The songs of the wind and the rivers returned slowly, and the land reshaped itself under their touch. The eruption had not only changed the air and the climate, it had rewritten the map of life. Old landscapes were erased, new ones began to form. The world that rose from the ashes of Toba was not the same as the one that came before. It was a reborn planet, carrying the faint echoes of what had been lost. In the long record of human history, volcanoes have erupted again and again, leaving behind scars not only on the land, but also on memory. They are reminders that the earth beneath us is alive, restless, and never fully still, and while none in recent centuries have matched the scale of Toba, their stories help us glimpse what such forces can do to the world we live in. In the year 1883, a small island in Indonesia called Krakatoa tore itself apart. For weeks it rumbled, releasing plumes of smoke that grew higher and thicker. On an August morning, the island finally erupted with such force that the sound was heard nearly 3,000 kilometers away. It was said to be the loudest sound ever carried through air. The explosion was so great that most of the island simply vanished, swallowed by the sea in a matter of hours. Tsunamis raced outward in all directions, some as high as the roofs of tall buildings, smashing into coastlines and drowning whole villages. Ships were thrown onto land. Thousands of lives ended in a single day. But Krakatoa's impact did not stop there. The fine ash it ejected rose into the upper atmosphere, spreading across the globe. Skies glowed red and purple in Europe and America months after the eruption. Painters at the time captured the eerie light in their canvases, sunsets that seemed almost unearthly. The average temperature of the earth dropped slightly, and harvests in distant countries suffered. The eruption of Krakatoa showed how even a small island could shake the planet. Only a few decades earlier, in 1815, another eruption had shaken the world in a different way. On the Indonesian island of Sumbawa, a mountain named Tambora erupted with staggering violence. It remains the largest volcanic eruption in recorded history. Villages around the mountain were buried beneath ash, and tens of thousands of people living nearby were killed outright. But Tambora's influence reached far beyond its own shores. The next year became known as the year without a summer. In North America and Europe, snow fell in June, frost struck in July and August, crops failed across continents and famine spread. Prices of food soared and people went hungry, even in lands untouched by ash. Dark skies and bitter cold inspired art and writing too, as the strange weather sank into the collective imagination. Some historians even link Tambora's cooling skies to the gloomy landscapes of painters and the birth of certain haunting stories written in candlelit rooms during unexpected frozen nights. More recently, in 1991, the world witnessed the eruption of Mount Pinatubo in the Philippines. Unlike Krakatoa or Tambora, Pinatubo unfolded in a time of satellites, cameras, and global communication. Scientists had enough warning to evacuate thousands, saving countless lives. When it finally erupted, the volcano shot ash and gases high into the stratosphere, where they spread around the planet. For nearly 2 years, the Earth's average temperature cooled by about half a degree. It was not enough to end harvests everywhere, but it was measurable from space. Weather patterns shifted, and delicate balances in rainfall were disturbed. It showed, with modern instruments, how one eruption could tilt the climate of the whole world. Krakatoa, Tambora, and Pinatubo stand as markers of the power locked beneath the earth. Each brought devastation to people nearby, and each altered skies and seasons far away. Yet even combined, their force does not reach the scale of Toba. Tambora released about 160 cubic kilometers of material, Krakatoa around 20, Pinatubo about 10, Toba in contrast expelled more than 2,800. That difference is almost beyond imagining. The smaller eruptions already shifted harvests, painted skies, and chilled the air for years. Toba's eruption multiplied that many times over. Where Krakatoa turned skies crimson for months, Toba darkened them for years. Where Tambora ended one summer, Toba may have ended dozens. And where Pinatubo could be measured in satellites and graphs, Toba's blast reshaped human destiny itself. The lessons from these more recent volcanoes are clear. The Earth does not need a supervolcano to change lives everywhere. Even smaller eruptions can ripple outward, touching every corner of the globe. Their stories give us glimpses of what happens when the sky itself becomes stained with ash, and they remind us that the line between stability and disruption is far thinner than we often believe. Across the world, in places separated by vast oceans and towering mountains, there are stories that echo one another, tales of fire raining from the heavens, legends of skies that turned dark and stayed that way, myths of floods that rose suddenly, sweeping away villages, animals, and entire ways of life. These stories, passed down for thousands of years, have long been seen as folklore. Yet when read carefully, they sometimes feel like faint memories of events so ancient that no written record remains. In many cultures, floods stand at the center of these myths. In Mesopotamia, along the Tigris and Euphrates rivers, the story of a great deluge was carved into clay tablets long before the tales of Noah's Ark appeared in later traditions. The Epic of Gilgamesh describes a flood so massive that it erased nearly everything. The gods, angered or afraid, unleashed waters that swallowed the land. Only one man, warned in advance, built a vessel to save himself, his family, and animals. Thousands of miles away in South America, there are legends among the Inca of a time when the rains did not stop and the seas rose higher and higher. Entire cities were drowned, and only those who fled into the mountains survived. On islands across the Pacific, from Polynesia to Hawaii, there are also stories of great waves and floods that reshaped the land. Some speak of gods battling in the sky, their conflict shaking the seas until the waters rose. Others describe storms so fierce that the ocean climbed the shores and never seemed to recede. In the highlands of Tibet, legends speak of an angry god who sent a flood to cover the valleys, sparing only those who climbed to sacred peaks. Fire, too, holds a place in ancient memory. Among Native American tribes of the Pacific Northwest, there are stories of mountains that once quarreled with each other, throwing fire and rock across the land. The people who told these tales may have been describing volcanic eruptions they witnessed, events so terrifying that they could only be explained through the language of myth. In New Zealand, Maori traditions tell of fire gods stirring beneath the earth, splitting mountains apart and darkening skies with smoke. In Icelandic sagas, eruptions were imagined as battles of giants, their fury painting the heavens red. It is striking how often darkness appears in these traditions. The Aztecs told of a sun that died, plunging the world into cold and shadow until a new sun was born. In Norse mythology, there is the tale of Fimbulwinter, a deep and endless cold that would fall upon the earth before the world itself was remade. In India, Ancient texts describe cycles of fire and flood, ages of destruction followed by renewal. Even in Aboriginal Australian traditions, there are stories of the sky itself turning black, leaving people wandering in confusion until the light returned. Oral traditions have a way of holding memory long after details blur. Each retelling shifts slightly, reshaped to fit the language and culture of those who speak it. But the core often remains: a flood that erased the land, a fire that fell from above, a darkness that stretched on far too long. It is possible that some of these stories are echoes of real events, filtered through the imagination of ancestors who had no other way to explain what they saw. When skies glowed red from ash, when the air was filled with choking dust, when rains lasted longer than anyone could recall, the only way to preserve the experience was to weave it into story. For small communities, storytelling was not just entertainment, it was a vessel for memory, carrying knowledge across generations. A tale of a flood might remind people not to settle too close to a river's edge. A myth of fire from the mountains might warn against building homes near restless peaks. A story of endless darkness might serve as a faint echo of what it meant to endure when the earth itself seemed against them. We cannot know for certain which myths trace back to the time of Toba's eruption or to other cataclysms that shook the planet. But when myths from cultures separated by continents all speak of waters rising, fires falling, and skies going dark, it is difficult not to wonder. Perhaps these stories are the last whispers of survival memory, carried forward not in stone or bone, but in the voices of parents telling their children what the world once was and what it could become again. When the skies finally began to clear, and the great shadow of the eruption slowly lifted, the world that remained was very different from the one our ancestors had known. Forests had thinned, grasslands had changed, and many animals had disappeared from the landscapes where people once hunted freely. What survived was scarred and reduced, yet still carried the possibility of renewal. In this fragile world, small groups of humans found ways to continue. Their recovery was not quick, measured not in years or even centuries but in long stretches of millennia. At first, survival must have been about the simplest choices: where to find food, how to stay warm, and which places still offered a chance at life. Along coastlines, people gathered shellfish, crabs, and seaweed. These resources were steady, even when inland plants withered and game animals grew scarce. The ocean, indifferent to the troubles of the land, still provided a living pantry. In caves and rock shelters, families learned to store what they could, stretching out their meager supplies to cover leaner times. As generations passed, these scattered groups began to expand once more. The human population, which may have dwindled to only a few thousand individuals, started to grow slowly. Children born into these families carried with them the fragile thread of continuity, each new life a small step away from extinction. But growth was uneven. Some regions could support people more easily than others, and so communities clustered in pockets where the land was kindest. These were refuges, places where conditions were less harsh and food could still be found. From these safe havens, humanity began its long journey of renewal. The pressure of scarcity forced creativity. Stone tools, once simple flakes and scrapers, became more refined. Evidence from archaeological sites shows the gradual shaping of blades and points, the careful working of stone to make implements sharper, lighter, and more versatile. Innovation was not always dramatic, but it was steady. Every improvement meant more efficient hunting, better cutting of hides, and greater chances of survival. Scarcity became a teacher, demanding adaptation at every turn. Fire also grew in importance. Though people had mastered it long before the eruption, its role deepened in the aftermath. It offered warmth during the colder years, protection in darker forests, and the ability to cook foods that would otherwise have been inedible. Around fires, families gathered at night, sharing stories and knowledge. Oral traditions strengthened bonds, carrying forward both warnings and wisdom. In times when so much was uncertain, memory itself became a tool for survival. Cooperation shaped recovery as much as any invention. Small bands of people learned that survival often depended on sharing rather than hoarding. Food gathered from the sea could be exchanged for meat hunted in the forest. Skills, too, were traded, as those who knew how to shape stone or track animals passed their abilities to others. These exchanges built fragile networks between groups, threads of connection that allowed knowledge and resources to spread beyond a single family or camp. Over time, such networks helped stabilize communities, making recovery possible on a larger scale. As the climate slowly balanced again, plants returned to once barren regions. Forests grew back, rivers cleared, and grasslands began to spread across valleys. With this renewal came the return of animals. Though many of the great beasts that once roamed freely were gone forever, humans adjusted to what remained, altering their hunting strategies and broadening their diets. Seeds, nuts, roots, and fruits became more important, woven into the daily search for nourishment. Millennia after the eruption, the human population was once again expanding across Africa and into Asia. Archaeological traces show footprints of movement, tools left behind in caves and evidence of fires long extinguished. Each trace is like a quiet signature, a record of resilience written in stone and soil. These remains tell us that recovery was not swift or easy, but it was unbroken. Scarcity never fully disappeared, and in some ways it remained a constant companion, yet it also became the spark for progress. With every challenge, people found new ways to adapt, to create, and to endure. The long road back was walked step by cautious step, but it carried humanity forward, away from the brink of disappearance and into the slow rise of growth that would eventually lead to all the complexity of life today. The modern world feels powerful beyond measure. From orbiting satellites to sprawling cities that glow through the night, humanity has reshaped the planet into a network of light and motion. We build towers taller than mountains of stone once carved by ancient hands. We move food, ideas, and energy around the globe faster than clouds can drift across the sky. Yet beneath this immense structure of progress lies a quiet paradox. The very systems that make us strong have also made us delicate. Our survival no longer rests on nature's mercy alone, but on an intricate web of human invention, a web that could tremble if even one strand is shaken. At the center of this web lies agriculture, the heartbeat of civilization. Every meal eaten today traces its story back to a field somewhere on Earth. Wheat ripens under the sun in one country, while rice paddies shimmer in another. Corn, soybeans, and countless crops flow through invisible pathways of trade to reach billions of plates. It is an astonishing achievement, but one built on balance, a balance of temperature, rainfall, and light that the planet provides freely. When that balance falters, as it did after great eruptions in the past, harvests fail. Humanity's greatest strength, the ability to feed so many, rests on the fragile constancy of weather and light. The earliest humans were wanderers, bound to no single landscape. If one region failed them, they moved to another. When rivers dried or herds vanished, they adapted, shifting their diets or finding new shelters. Their lives were uncertain but resilient, flexible enough to bend without breaking. Today, humanity is rooted. Our cities cannot migrate. Our farms are locked to their soils. Our supply chains stretch across oceans, linking faraway fields to the tables of distant nations. This interconnection has brought abundance and security, but it has also tethered our fate to the stability of the whole. Trade, once a luxury, has become a lifeline. Nations rely not only on their own harvests, but on the harvests of others. Grain grown in one hemisphere feeds people in another. Energy mined from the earth in one region powers the factories and homes of countless others. A single port closure, a drought in a faraway country, or a disruption to global transport can ripple outward, touching corners of the world that seem far removed. The strength of this global network lies in its reach, but its fragility lies there too. When every system is connected, none stands alone when strain begins to spread. Energy is another thread in this vast dependence. The warmth in our homes, the glow of our lights, the movement of our machines, All flow from sources that must remain constant: coal, oil, gas, nuclear power, solar, and wind each tie us to the stability of the environment. Solar panels need clear skies. Wind turbines need predictable currents. Even the most advanced technologies rely on the rhythm of the planet, a veil of volcanic ash, like the one Toba once cast across the world, would scatter sunlight and cool the air, altering winds and rainfall patterns. The power grids of the world would feel that change. The systems that hum quietly beneath our feet would suddenly become fragile, strained by shifts they were never designed to endure. And yet it is not a story of weakness alone. Humanity's strength has always been found in ingenuity. We have learned to grow food in deserts, to desalinate oceans, to communicate across entire hemispheres. We carry the wisdom of our ancestors and the knowledge of our sciences, but this progress has come with a hidden cost: the loss of independence from the very systems we built to protect us. Each advance has tied us more closely to the next, until survival itself has become collective, shared across the entire planet. If the Earth were to test us again, the challenge would not come as isolation, but as interdependence. Billions of lives are woven into one global pattern, so that the strain on a single thread would vibrate through all the rest. We are stronger than we have ever been, yet our resilience depends on the same complexity that could one day undo us. This is the paradox of modern humanity, that strength and fragility now share the same roots. We have learned to command rivers, harness lightning, and cultivate the land on a planetary scale. But in doing so, we have placed our faith in the delicate harmony of systems that must never fail. The lesson of the past, of Toba and the long winters that followed, is still quietly written beneath our progress. We are not beyond nature. We are bound to it more tightly than ever before. Beneath the calm waters of Lake Toba in Sumatra, there is a silence that is not entirely peaceful. The lake looks serene, stretching more than 100 kilometers from end to end, its surface broken only by small islands and drifting boats. To visitors it is a place of beauty, a blue mirror set against green hills. Yet under that stillness lies a vast scar in the Earth's crust, the remnant of the eruption that shook the planet 74,000 years ago. Scientists return again and again to this place, not just to study what happened in the past, but to ask a more unsettling question: could it happen again? Volcanologists watch Toba carefully. Sensors measure the way the ground shifts by tiny amounts, rising and falling as if the Earth is breathing. Satellites track the heat rising from beneath the surface, and instruments capture the gases that escape quietly from vents in the region. These signs, taken together, offer hints about what might be happening deep underground. The magma chamber that once exploded with unimaginable force is still there, far below the surface. It is not empty. Over thousands of years, molten rock continues to move, slowly refilling the chamber in a process that could last millennia. For now, the system rests, but history has shown that rest does not mean safety. Toba is not alone. The Earth holds other giants in waiting, each one with the potential to unleash an eruption on a scale that dwarfs anything seen in recorded history. One of the most studied lies in the heart of North America, Yellowstone. Visitors walk among its hot springs and geysers, marveling at the boiling pools and the steam rising into the air. These sites are not just tourist wonders, they are signs of a vast heat source beneath the crust. Yellowstone has erupted 3 times in the last 2 million years, each eruption spreading ash across much of the continent. Scientists know it will erupt again, though no one can say when. Far to the south, in New Zealand, lies Taupo. This caldera erupted about 26,000 years ago, one of the most violent volcanic events since Toba. The eruption reshaped the land and left behind a massive lake. Much like Toba's, even in more recent centuries, Taupo has shown its restlessness with smaller eruptions, reminding those who live nearby that the forces beneath the earth have not gone quiet. Closer to Europe, in Italy, the Campi Flegrei caldera stirs uneasily. Known as the Fields of Fire, this region is marked by hot ground, steaming vents, and restless activity beneath Naples. Unlike Yellowstone or Toba, Campiflegrei lies near a densely populated area. Scientists worry that even a modest eruption here could endanger millions. Though not as large as Toba, its potential impact on modern civilization is immense. When geologists study these supervolcanoes, they look at cycles of time far longer than human lifespans. They study layers of ash, ancient lava flows, and chemical signatures locked in stone. These records show that catastrophe is not an exception to Earth's history, but part of its rhythm. Supereruptions are rare, measured not in centuries but in hundreds of thousands of years. Yet on the scale of geological time, they are regular, recurring events. The Earth builds pressure, releases it in violent bursts, then begins the cycle again. The knowledge that such cycles exist brings both clarity and unease. Humanity has flourished during a time of relative calm, an interlude between great eruptions. The silence of Toba, Yellowstone, Topo, and Campiflegrei is not permanent. It is only a pause in a story that has unfolded countless times before us. The same forces that once darkened the skies and chilled the earth remain at work beneath our feet, moving slowly, invisibly, on a clock that does not match our own. Scientists do not look for certainty, because certainty is not possible. Instead, they search for signs, for patterns that might offer warning. They hope that by understanding the cycles of the past, they may one day recognize the early whispers of another eruption. For now, the giants remain asleep, their power hidden beneath calm lakes and steaming fields. Yet the Earth has always spoken in cycles, and those cycles remind us that nothing on this planet rests forever. If you found yourself captivated by this journey through Earth's most profound moments of transformation, I'd be deeply grateful if you subscribed to Simply About Earth. Your support helps us continue exploring these stories that connect us all to our planet's incredible history. In the quiet landscapes where supervolcanoes sleep, the Earth still whispers. To the untrained eye, a lake like Toba or a meadow above Yellowstone looks still and harmless. But beneath those calm surfaces are restless systems that shift and stir. Scientists have learned to listen for the faint signals that sometimes rise from the deep, signs that pressure is moving, that magma is stirring, that something hidden is alive. These signals are not always loud or obvious. They come in patterns of tremors, in the gentle rise of land, or in the invisible breath of gases escaping into the air. One of the clearest signs of movement beneath a volcano is seismic activity. The Earth's crust is not rigid but fractured and filled with pathways. When magma forces its way through those cracks, it creates small earthquakes. These are often too faint to be felt by people, but sensitive instruments detect them. A single tremor might mean little, but when dozens or hundreds cluster together, forming what scientists call a seismic swarm, it suggests that molten rock is on the move. These swarms sometimes precede eruptions as the Earth shudders and adjusts to pressure building below. Yet not every swarm ends in disaster. Some fade quietly, leaving only questions behind. Ground movement is another clue. Imagine a pot of water heating on a stove, its lid slowly lifting as steam builds. A volcano can behave in much the same way. As magma rises, it pushes upward, and the surface above begins to swell. Using satellites and ground-based instruments, scientists measure these shifts, sometimes only a few centimeters over many months. Around Yellowstone, for instance, the land has lifted and sunk in cycles, sometimes rising more than half a meter before settling back down. These changes show that the system is alive, but they do not guarantee an eruption. Like the breath of a giant beneath a blanket, the ground shifts without always breaking open. Then there are the gases, the hidden exhalations of magma. Deep underground, molten rock releases carbon dioxide, sulfur dioxide, and water vapor. These gases travel upward through cracks, escaping at the surface in hot springs, fumaroles, and steaming pools. Scientists track their amounts carefully. A sudden increase in sulfur dioxide, for example, can mean that fresh magma has risen closer to the surface. At times, changes in gas chemistry reveal that magma chambers are mixing or refilling. The air around these landscapes becomes a kind of diary of the Earth's hidden movements, though reading it requires careful study. Together, earthquakes, swelling, and gases form the main tools for watching the giants beneath us. They are the closest humanity has to a warning system, but prediction is never simple. Volcanoes are not machines with neat dials to read. They are complex systems, each with its own personality, and no two eruptions follow the same script. Some great eruptions are preceded by dramatic signs, while others arrive after quiet build-up. Even with the most advanced monitoring, certainty remains out of reach. Supervolcanoes add an even greater challenge. Their magma chambers are vast, stretching for tens of kilometers, and their eruptions unfold on timescales far beyond human lifespans. A seismic swarm today may not mean an eruption tomorrow or even in the next century. The swelling of land might last for decades, then ease without breaking through. Gases might surge and fall again, reflecting movements deep below that never reach the surface. For scientists, the puzzle lies in deciding which signs mark ordinary restlessness and which herald the beginning of catastrophe. To improve their understanding, researchers study smaller eruptions around the world. By comparing patterns of earthquakes, swelling, and gases before known eruptions, they hope to find common threads. Computer models simulate how magma might rise and how the crust might respond, offering glimpses of possible futures. Ice cores and rock layers reveal what past eruptions left behind, showing how the planet reacted and how quickly changes spread. Each clue adds a fragment to the larger picture, but the full image remains unfinished. The uncertainty is both humbling and sobering. In a world where satellites can map the surface of Mars and probes can touch the edges of the solar system, the forces beneath our own feet remain elusive. The giants of the Earth speak in tremors and whispers, and even with all our instruments we cannot always tell what they are saying. What scientists do know is that vigilance matters. Continuous monitoring means that if signs grow stronger, there may be time to prepare, even if no prediction can be perfect. For now, the supervolcanoes rest in uneasy silence. Their signals flicker, their surfaces shift, and their gases rise in steady streams. The work of prediction continues, an effort not to conquer the Earth's power, but to listen, to watch, and to learn what the planet may one day choose to reveal. In the spring of the year 2010, a mountain in Iceland reminded the world of how fragile our systems can be. The name of that mountain, Eyjafjallajökull, is difficult for many outside Iceland to pronounce, but its eruption left an imprint far beyond its frozen slopes. The eruption itself was not enormous by the standards of geology, yet the ash it threw into the skies drifted across Europe and created a disruption unlike anything most people had seen before. The ash cloud moved silently, carried on the wind until it spread across some of the busiest air routes on Earth. For days and then weeks, airports closed, thousands of flights were cancelled, millions of travelers stranded. Businesses that relied on air cargo suddenly found their supply lines broken. Flowers from Kenya, fresh seafood from the Atlantic, and electronics from Asia never made it to their destinations. The disruption cost billions of dollars, yet it all began with a relatively small eruption. This event was only a faint glimpse of what might happen if the world faced something on the scale of Toba. Volcanic ash is not soft powder. It is made of sharp fragments of rock and glass, ground so fine that it drifts like smoke, but retains the hardness of stone. When it enters the jet engines of an aircraft, it melts in the high heat, then hardens again on cooler surfaces, choking turbines and shutting down power. This is why flights cannot move through ash clouds. It is not just a matter of visibility, it is a matter of survival. If a super eruption spread ash across continents, the grounding of planes would not last weeks but years. Entire economies that depend on fast global transport would slow to a crawl. Food supply chains would feel the strain almost immediately. Modern agriculture is vast, but it is also fragile. Crops are often grown far from the places where they are eaten, then shipped across oceans and continents. If planes were grounded and shipping routes slowed by ash settling into harbors, Many regions would face shortages. Wheat from one part of the world, rice from another, and maize from yet another might never arrive on time. Nations that rely on imports would be the first to feel hunger, but even surplus regions would suffer as markets twisted and prices rose. Ashfall itself damages agriculture directly. When fine ash settles on fields, it clogs the pores of leaves, preventing plants from breathing. It weighs down crops until stems break, and when mixed with rain it turns to a heavy sludge that can smother entire harvests. Rivers and irrigation channels choke with sediment, turning once clear waters into grey flows that poison fish and ruin farmland. Livestock grazing on fields covered with ash can die from internal damage as the sharp particles tear their insides. The effects would not stop at the farm. Power grids are also vulnerable to volcanic ash. When ash coats transformers and insulators, it conducts electricity poorly, causing short circuits and failures. After eruptions in the past, engineers have had to scrape ash from delicate equipment by hand to keep power flowing. In a super eruption, the sheer volume would overwhelm these systems. Blackouts could stretch across cities, silencing lights, machines, and communication networks. Satellites orbiting high above the Earth might seem safe, but even they could be affected. Ash and sulfur aerosols reaching the stratosphere can interfere with radio signals, distort satellite imaging, and scatter the sunlight that solar panels rely on. In addition, the cooling of the atmosphere caused by volcanic aerosols can change how air currents move, which alters the drag on satellites and shifts their orbits. Navigation, weather forecasting, and even the global internet connections that run through satellite relays could falter. Air travel, power grids, and satellites together form the nervous system of modern civilization. They connect people across continents, power industries, and allow knowledge to flow at the speed of light. Each of them is vulnerable to volcanic ash. The events of Eyjafjallajökull in 2010 showed how quickly the chain can weaken even from a moderate eruption. That ash cloud stranded travelers and shook economies, yet it was only a small taste of what could come. A super eruption sending ash across hemispheres would not pause flights for weeks, but cut the threads of connection for years. In the silence that would follow, cities would dim, communication would falter, and the great networks that hold humanity together would thin and strain. All of it, from the markets to the skies, could be reshaped by something as simple as fine grey dust falling softly from above. When a mountain like Toba were to erupt again, the world would have little choice but to face a test unlike any in recorded history. The question of preparedness lingers uneasily, for while humanity has drawn up plans for many disasters from earthquakes to tsunamis, the scale of a super eruption stretches far beyond ordinary imagination. The idea of preparing for centuries of disruption does not fit easily into the way nations usually plan for danger. There are monitoring networks in place today around the world. Volcanologists keep watch on restless giants with seismographs, gas detectors, and satellites that measure the slightest lift of the land. Yellowstone is studied closely in the United States, Taupo in New Zealand, and Campi Flegrei in Italy. Lake Toba itself is observed by Indonesian scientists with international support. These efforts aim to catch the early signs of movement, to raise alarms if magma begins to rise. Yet knowing that an eruption is possible is not the same as being prepared for what follows. Most emergency plans for volcanoes focus on local effects. Evacuations from valleys where ash will fall thickest, movement of people away from rivers at risk of flooding from melted ice or sudden mud flows, and air traffic restrictions near plumes. These are important, but they are designed for eruptions on the scale of Pinatubo in 1991 or Eyjafjallajökull in 2010. A super eruption spreading ash across continents would overwhelm such measures within days. Global organizations such as the United Nations recognize supervolcanoes as potential threats, but they do not yet command the same attention as asteroids or climate change. Part of the reason lies in rarity. Super eruptions occur on timescales measured in hundreds of thousands of years, so the immediate urgency feels low compared to rising seas or melting ice. Another reason is the difficulty of planning for something so long-lasting. A flood or earthquake may destroy a region, but recovery begins within months or years. A super-eruption could cloud the skies for decades and alter climates for centuries. Food security is one of the greatest concerns. International agencies have built stockpiles for short-term crises. The World Food Programme moves supplies quickly during famines or conflicts, but those reserves are measured in months, not decades. A super-eruption would cut sunlight to crops year after year, forcing humanity to rethink farming entirely. Scientists have considered indoor agriculture powered by artificial light, but the scale required to feed billions would demand resources far beyond what is available today. Energy grids are another weak point. Engineers can respond to storms and earthquakes, but they do not have plans for ash blanketing entire continents. Clearing ash from transformers and power lines is possible after a small eruption, but when the dust falls for months or years, maintenance crews could never keep up. Blackouts would spread, cutting communication and transport just when coordination mattered most. Some researchers suggest building international seed vaults and food reserves deep underground, places where supplies could be shielded from ash and cold for centuries. The Svalbard Global Seed Vault in Norway is one such effort, preserving seeds of thousands of crops inside a mountain. But a seed vault is not a farm, and planting those seeds in a world without reliable sunlight would be another challenge entirely. Preparedness also struggles against politics and resources. Nations already wrestle with immediate problems like poverty, disease, and climate change. Convincing governments to spend billions preparing for a disaster that may not arrive for many generations is difficult. Plans for super-eruptions often remain in the realm of academic papers and conferences, rather than becoming binding global policies. The truth is that preparing for centuries of disruption runs against the way humans think. People plan in spans of years, sometimes decades. Governments think in terms of election cycles, companies in quarters, families in lifetimes. To plan for centuries means stepping outside the ordinary frame of human concern. It means imagining a future where entire generations grow up under dim skies, where global trade is remade, and where survival depends on cooperation at a level never before seen. For now, humanity's emergency plans remain partial, focused on the short term and shaped by the scale of disasters already experienced. What lies beyond that scale, in the silence of supervolcanoes, is still largely unplanned. When the great eruption of Toba spread its ash across the world, it did not only darken the skies, it thinned the ranks of humanity itself, stripping our species down to a thread of survival so narrow that it is difficult to imagine. Scientists studying the echoes of that time often speak in numbers, because numbers give shape to what words alone cannot carry. The numbers are small, shockingly small, and they remind us how close we once came to being erased. Genetic evidence suggests that after the eruption, the total number of humans alive may have dropped to only a few thousand. Imagine the entire human race fitting into a single small town, every family on Earth reduced to a cluster of survivors clinging to life. These people lived scattered across Africa and parts of Asia, their groups separated by distance but united by the same struggle to endure. Some researchers believe the population may have been as low as 2,000 breeding individuals. Others allow for 10,000. Either way, the figure is a shadow of the billions alive today. When scientists compare this to endangered species, the parallel becomes striking. The mountain gorilla, for example, hovers around 1,000 individuals in the wild, its future always uncertain. The giant panda, once reduced to a few thousand, has only recently begun to recover through protection and conservation. Cheetahs, with fewer than 7,000 left, suffer from low genetic diversity that makes them vulnerable to disease and environmental change. These animals today live on the razor's edge, their future balancing on small numbers. For a time, humanity stood in that same place. A population this small carries dangers beyond hunger and cold. With so few people, genetic diversity narrows. Imagine shuffling a deck of cards, but with many of the cards missing, the hands that can be dealt are fewer, the combinations more limited. In human terms, this means that traits once common might have disappeared entirely, and weaknesses could have spread unchecked. A disease could have swept through with little resistance. A famine in one region could have ended entire family lines. Survival depended not only on finding food and shelter, but also on luck and resilience encoded in fragile strands of DNA. The very shape of humanity may have been altered by this bottleneck. Geneticists searching through the code of modern humans see patterns that hint at this time of near extinction. Mutations shared across nearly all people alive today suggest that our ancestors passed through a narrow gate, leaving behind only a portion of the diversity that once existed. It is as if the great fire of Toba burned away countless branches of our tree, leaving only a few shoots to carry forward. To picture the fragility, imagine an endangered species today. If the last few thousand snow leopards vanished, their silence would be final. If the last sea turtles were lost, no number of memories or photographs could bring them back. Humanity itself once stood that close to vanishing. A single failed season, a single epidemic, or a single twist of chance could have ended the line entirely. That it did not is a reminder that survival sometimes depends on the narrowest of margins. The head count of survival is more than a number. Each of those few thousand individuals carried the spark of life forward. Each was part of a family, a small group navigating landscapes changed by ash and cold. Children born into those families were not just heirs to their parents, they were the fragile continuation of an entire species. The survival of humanity rested on the shoulders of those who endured, who found ways to gather food from a stripped land, who remembered where the water still ran clear, and who kept moving when staying in one place meant death. The numbers remind us that we were not always as numerous or as secure as we are today. There was a time when humanity itself was an endangered species, as precarious as the most vulnerable animals alive in the present. The razor's edge of survival can be measured in head counts, and for us that head count once fell so low that every birth, every small success mattered to the story of all who came after. The story of Toba's eruption is written not only in the earth but within us. Every living person carries a silent record of survival written in the language of DNA. Inside each cell lies a code that has endured volcanic winters, ice ages, droughts, and disease. It is a library of adaptation built by countless generations who lived through times when existence itself was uncertain. Long after the ash settled, the echoes of that survival remained, not in stone but in the chemistry of our bodies. Scientists today can read this buried history. Advances in genetics have made it possible to trace how humanity's ancient trials shaped the traits we still carry. These discoveries do not only reveal where we came from, but how the human body became what it is. Modern studies of genomes across the world show that many features of our immune systems, metabolism, and even behavior can be traced back to the small group of ancestors who endured the aftermath of Toba's eruption. The immune system is one of the clearest windows into this legacy. During the long cold years that followed the eruption, disease would have been a constant threat. Populations already weakened by hunger and exposure were vulnerable to infections. Only those with certain genetic defenses could have survived repeated epidemics. Over thousands of generations, those protective mutations became common across humanity. Scientists studying the human leukocyte antigen complex, the group of genes that helps our bodies recognize and fight pathogens, have found traces of these ancient pressures. Some of the immune responses we rely on today, from how we react to viruses to how we resist bacterial infections, carry the faint imprint of those early survivors. The same is true of how we eat, store, and use energy. The world after Toba was harsh and unpredictable. Food sources were scattered and unreliable, and starvation was an ever-present danger. Genetic traits that made it easier to conserve calories or store fat would have been life-saving advantages. Researchers have found variations in genes related to metabolism and insulin regulation that may have originated in times of scarcity. These variations, once vital for endurance, now shape how modern humans respond to abundance. influencing our tendency to store energy efficiently, a trait that once ensured survival, but today can lead to health challenges like obesity or diabetes. The past still whispers in our cells every time our bodies decide how to use the food we eat. Adaptation also took subtler forms. As humans spread into new environments after the eruption, groups evolved specialized traits suited to the lands they settled. Populations living in high mountain regions, such as the Himalayas and the Andes, develop genetic changes that help them thrive where oxygen is thin. Variants in genes controlling hemoglobin production allow their blood to carry oxygen more efficiently, preventing fatigue or illness in the cold, rarefied air. Others who lived in cold regions developed genes that improve their ability to generate and retain body heat, changes that echo the challenges faced by those who first walked through the frozen shadows of Toba's long winter. Even aspects of human behavior may trace back to that narrow moment in history when survival depends on cooperation. Social bonds become as important as food or shelter. In small, isolated groups, empathy and communication would have been essential. Modern research suggests that some genetic variations influence levels of oxytocin and serotonin, chemicals that affect trust, bonding, and emotional connection. These traits, shaped by the need to survive together, may have been passed forward, gradually weaving cooperation into the human blueprint. Modern genetics continues to uncover these deep connections. Each discovery reveals not just how humans survived Toba, but how that survival sculpted our biology. The scars of the past are not visible, yet they exist in the way our bodies fight infection, manage energy, adapt to new heights, and seek connection with one another. We are built from layers of inherited resilience, each one a trace of an ancient challenge overcome. When we look at humanity today, we are seeing the culmination of those ancient victories. Every heartbeat carries the rhythm of adaptation that began in the shadows of catastrophe. Our immune systems still remember ancient plagues. Our metabolism still conserves energy as if famine might return. Our social instincts still reflect a time when survival meant trust and unity. We are, in a very real sense, living fossils, not of bone or stone, but of endurance. Within us lies the evidence of the world's near ending, and its rebirth. Our genes are a testament to those who endured the silence after the eruption, who passed forward not only life, but the tools to preserve it. The story of Toba is written in the ash of the earth, but the proof that it was survived is written in us. When the ash of Toba finally settled, and the world began to breathe again, the humans who remained faced a planet that seemed both empty and uncertain. The forests that had once offered fruit and shelter were thin and silent. The sky still held a faint haze, a reminder of what had nearly ended them, yet somehow they endured, and in doing so became something new. Humanity did not simply survive that darkness, it was shaped by it. From that long trial emerged a species defined not only by intelligence, but by resilience woven into its very identity. Resilience is more than endurance. It is the ability to take hardship and turn it into memory, into knowledge, into strength. Even when the world grew unpredictable, people learned to record what mattered, not with ink or symbols, but with words and rhythm. Around fires or beneath starlit skies, the first storytellers passed down the lessons that had kept them alive. Which plants could still be eaten, which paths led to clean water, which seasons brought safety, and which carried danger. These stories were not entertainment but lifelines. Through repetition, the fragile wisdom of one generation became the survival manual of the next. Over time, memory evolved into something deeper, a collective inheritance of knowledge that reached beyond simple survival. People began to tell stories not just about how to live, but about why they must. Tales of ancestors, of spirits, of cycles of destruction and renewal grew out of lived experience. These stories preserved more than facts. They preserved perspective. They reminded small, scattered groups that their suffering was part of a greater rhythm, and that endurance itself had meaning. This act of remembering became humanity's first great technology. Long before the first tools of metal, the first cities, or the first written marks on clay, The ability to preserve memory through story allowed humans to extend their minds across time. The lessons of one lifetime no longer vanished with death. They could travel forward, accumulating, adapting, and growing. That transfer of wisdom turned survival into progress. Cooperation, too, evolved into something more profound than necessity. Earlier, it had been about hunting together, or sharing food to endure the cold. But in the long centuries after the eruption, cooperation became the very structure of human society. Individuals learned that their strength was magnified through unity, that the group was not simply protection but identity. People formed alliances that extended beyond bloodlines. They traded, shared tools, exchanged language, and began to trust strangers. That widening circle of cooperation laid the groundwork for civilization itself. As generations passed, this cooperative instinct intertwined with culture and imagination. Humans developed rituals, songs, and symbols to mark their shared existence. These expressions gave shape to emotion and bound communities together. Grief, hope, and gratitude became shared experiences, linking people across distance and time. Through these bonds, resilience became self-sustaining. A community could fall, but its stories and customs could survive elsewhere, carried in the voices of travelers or the memories of children. Innovation followed naturally from this collective spirit. The human capacity to adapt did not end when the world warmed again. Instead, it became an enduring habit. Every challenge sparked curiosity rather than surrender. When the land changed, people invented new tools, new methods, new ways to read the signs of nature. Curiosity became an evolutionary advantage, ensuring that when disaster struck again, and it always did, humanity would meet it not only with fear but with invention. Perhaps the most remarkable adaptation, however, was emotional resilience. The survivors of Toba lived with uncertainty that stretched for generations. Yet even in despair they found meaning. They created art, painted on stone walls, and buried their dead with care. These acts did not provide food or shelter, but they nourished something equally vital, a sense of continuity, the belief that life, though fragile, was still worth preserving. In this quiet defiance of despair, humanity revealed its most enduring strength. By the time the earth healed and the skies cleared, our species had become something unbreakable in spirit. Resilience was no longer just a reaction to hardship, but a defining trait. Memory became tradition, cooperation became culture, curiosity became innovation, and endurance became identity. We often measure progress in inventions or discoveries, but the true foundation of humanity lies in this invisible inheritance, the instinct to persist, to remember, and to rebuild. From the ashes of Toba's eruption, humanity learned that survival is not just about living through catastrophe. It is about carrying forward the memory of endurance itself, so that every generation, even in peace, remembers how to begin again. In many places across the world, people wake each morning with no thought that they live upon a giant. Beneath their feet lie chambers of molten rock large enough to swallow mountains, yet on the surface the world appears calm. Supervolcanoes, though rare and sleeping, are not confined to ancient history. They remain with us, their calderas filled with lakes, forests, or meadows where daily life continues as though nothing stirs below. One of the most famous of these giants lies in the western United States. Yellowstone National Park stretches across a wide plateau, home to steaming geysers, boiling hot springs, and sulfur-scented pools of brilliant colors. Tourists visit by the millions each year, drawn by sights that seem otherworldly. Families walk on boardwalks above bubbling ground, unaware that all of these features are connected to a vast system of heat and pressure beneath the park. Yellowstone is not a single mountain with a classic cone but a caldera, a collapsed bowl formed from ancient eruptions. The scale is almost too large to recognize without a map. Instead of a peak, visitors see wide valleys, ridges, and lakes that hide the scars of events far older than any human memory. Scientists have traced at least 3 super eruptions here, each of them powerful enough to alter climates around the globe. Today, however, Yellowstone wears a mask of beauty. Elk graze in meadows, wolves move through forests, tourists gather at dawn to watch Old Faithful send a plume of boiling water high into the air. It is a place where danger and wonder are inseparably linked. Living near Yellowstone means carrying a distant awareness of its potential. Towns in Wyoming, Montana, and Idaho depend on tourism, ranching, and forestry. For many residents, the park is both a source of livelihood and identity. The threat of a super eruption is so remote in human timescales that daily life rarely bends beneath it. Yet instruments buried in the ground and satellites above constantly track its breath. Small earthquakes rattle the park by the thousands each year, often too faint to feel, reminding scientists that the system is alive, if not awake. Half a world away, in Sumatra, another supervolcano holds a quieter presence. Lake Toba, the scar left by one of the largest eruptions in Earth's history, now stretches more than 100 kilometers across. It appears as a serene body of water, rimmed by forested mountains. The lake itself shimmers with changing light, calm on some days, stormy on others. To anyone visiting for the first time, it might seem like nothing more than a peaceful retreat, a place of beauty carved by nature. Yet beneath the waters lies a memory of ash and fire that once nearly ended humanity. Around Lake Toba, villages rise along the shores, fishing boats rest against docks, their nets drying in the sun. Children play by the water's edge. Farmers grow crops in soil made rich by ancient volcanic deposits. For the Batak people who have lived in the region for centuries, the lake is not only a landmark but a home, woven into stories, rituals, and traditions. The eruption that formed it belongs to a time too distant to hold in memory, so life continues with the rhythm of planting, harvesting, and fishing, all carried out under the silent presence of the caldera. To live beside Lake Toba is to rely on the gifts left behind by catastrophe. Volcanic soil is fertile, producing rice, vegetables, and fruit. The lake offers fish that sustain families. The surrounding mountains draw visitors from around the world, bringing income through tourism. Just as with Yellowstone, danger is both hidden and constant, but it is folded into everyday life until it becomes background, no more pressing than a distant storm. Supervolcanoes, though they hold the potential for unimaginable change, are also landscapes of present beauty and human endurance. People build homes by their shores, graze animals on their slopes, and walk along their steaming valleys without fear. The giants sleep, and while they do, life settles over them in layers of habit, culture, and hope. The earth remembers the violence, but those who live upon it see only the surface, calm for now, and carry on with the ordinary acts of living that tie generations to a place. Imagine waking to a dawn that never fully arrives. The air carries a strange stillness, and the horizon glows faintly red, not from sunlight, but from ash illuminated by a dim, broken sky. Fine grey particles drift downward, settling on everything: fields, cities, rivers, and the roofs of homes. In the first days, people might stare upward in confusion. Within weeks, they would realize that the world they knew had ended. Scientists have modeled this scenario many times, not as fiction, but as a way to understand how societies would react if a supervolcano erupted in the modern world. The immediate environmental effects are well understood. Temperatures would plummet, sunlight would fade, and seasons would collapse into a long volcanic winter. But what comes after? The human response is harder to predict. It would not only be a test of infrastructure, but of civilization itself. The first tremors of disruption would begin with food, as fields turned barren and harvests failed. But beyond hunger lies something deeper: the unraveling of order. People do not face disaster as isolated individuals anymore. Nearly 8 billion of us are tied together through governments, economies, and systems of trade. When one thread breaks, the tension spreads through all the others. Within months, nations would face decisions that could shape history. Governments would attempt to control food reserves, regulate movement, and maintain authority over frightened populations. In some regions, rationing might keep panic at bay for a time. In others, shortages and rumors could ignite chaos. Long lines for bread and water might become the new symbol of survival. Social trust, the invisible fabric that holds communities together, would fray with each misdirected promise, each empty shelf. Migration would follow, as it always has in times of crisis. Families would leave regions where crops no longer grow, moving towards zones with remaining warmth or stored supplies. The scale would dwarf any movement in recorded history. Millions, perhaps hundreds of millions, traveling by road or foot, seeking stability in a collapsing world. Borders would become flashpoints. Nations might seal themselves off, unable to feed both citizens and refugees. Humanitarian corridors could form briefly, only to close again under the strain. In some places, kindness would prevail. In others, fear would decide who lives and who starves. Power structures would begin to shift. Countries that control vital resources, fertile soil, access to clean water, or existing food stockpiles would suddenly find themselves holding the balance of global influence. Alliances might fracture as leaders prioritize their own survival over old treaties. The global economy, dependent on trust and movement, would contract sharply. Currencies could lose value, replaced by barter or digital trade networks limited to surviving infrastructures. The age of global abundance would give way to one of guarded scarcity. Cities, once centers of progress, would become fragile ecosystems of desperation. Urban life depends on constant inflows of energy and food. Without them, cities turn from homes into traps. Crowds would gather in public spaces, demanding action, demanding answers. The tension between citizens and governments would rise with each passing week. In some countries, authoritarian control might tighten. In others, states could collapse altogether, leaving regions to govern themselves. New local powers might emerge, formed not by election but by necessity, communities led by those who can provide stability or security. Conflict would not be limited to the physical. The psychological impact of global dimming would weigh heavily. Humans evolved under sunlight, and the loss of natural light would change behavior profoundly. Rates of depression, anxiety, and violence would rise. In the absence of clear information, misinformation could spread rapidly, deepening divisions. The struggle for truth might become as fierce as the struggle for food. Amid all this, small lights of resilience would still appear. Communities would form cooperative networks to share resources. Some might return to traditional methods of preservation, smoking, drying, and fermenting food. Others might turn underground, creating shelters lit by artificial lamps, growing crops in improvised greenhouses, powered by what remains of the grid. Technology would not save everyone, but in scattered places it could buy time. Religion and culture would evolve quickly under pressure. Some would interpret the eruption as divine punishment, others as a cycle of nature repeating itself. Shared belief could unite communities or divide them, depending on what stories take root. The capacity for faith, whether in gods or in human ingenuity, would once again become a survival tool. If a supervolcano erupted tomorrow, humanity would face more than an environmental catastrophe. It would face a mirror, one reflecting our interdependence and our fragility. The eruption itself might last only days, but the aftermath could stretch across generations. Children born in its shadow might grow up never knowing a blue sky. The test would not only be whether civilization could endure, but whether compassion could, because in the end, survival would not depend solely on who has the most food, or the strongest walls, or the largest armies. It would depend on whether humanity remembers what kept us alive the first time the skies went dark, the ability to come together when everything else falls apart. The Earth has always moved in rhythms that are far greater than human lifetimes. To us, centuries feel long and millennia almost impossible to grasp. But to the planet, even millions of years are only passing moments. Within this deep time, patterns unfold, patterns of creation and destruction that have shaped the course of life again and again. Among the most powerful of these are the great volcanic upheavals, the super-eruptions that scar the land and darken the sky. A supervolcano is not simply an oversized mountain, it is a force woven into the planet's deepest layers, linked to the slow movement of tectonic plates, the circulation of heat from the Earth's core, and the endless recycling of crust and mantle. When one erupts, the event is not isolated, it is part of a greater cycle, tied to the history of life itself. These colossal blasts have the power to strip the world of light, cool oceans, wither forests, and wipe away species that have thrived for millions of years. Yet strangely, they also open the door for something new to emerge. Scientists studying the fossil record find signs of these cycles imprinted in stone. Extinction events, where vast numbers of species vanish, often align with catastrophic volcanic activity. In Siberia, over 250 million years ago, immense volcanic eruptions poured out rivers of lava that stretched for thousands of kilometers. This time in history, known as the Great Dying, saw the loss of nearly all marine life and most creatures on land. The skies would have been heavy with ash, the seas poisoned with chemicals leached from the rocks, and ecosystems pushed beyond the edge of recovery. Yet after this collapse, new forms of life appeared. Ancient reptiles gave way to the first dinosaurs, and in the oceans survivors carved out entirely new niches. Far later, another great series of eruptions built the Deccan Traps in what is now India. These eruptions coincided with the end of the age of dinosaurs. The world was already reeling from the impact of an asteroid, but the eruptions deepened the crisis. Lava flooded the land in layers that reached more than 2 kilometers thick. Gases filled the atmosphere, shifting climates and stressing ecosystems already in decline. In the wake of this double catastrophe, the dinosaurs disappeared and mammals began their slow rise toward dominance. What is striking is not only the scale of destruction but also the renewal that followed. The Earth seems to have its own rhythm of erasure and rebirth. The ash and lava that once suffocated landscapes eventually hardened into fertile soils. Forests grew again, nourished by minerals released in the fire. Where old species vanished, others adapted and spread into the open spaces left behind. Over time, the scars of catastrophe became the foundations for entirely new worlds. This pattern is not one of cruelty, nor of mercy. It is the impartial rhythm of geology and biology intertwined. Life bends and breaks, but it also seizes every chance to return, to reimagine itself in forms never seen before. Without these cycles, perhaps humans would never have existed. The path from ancient fishes to mammals to us was shaped not only by slow evolution, but also by sudden upheaval that cleared the stage for new players to rise. Even super-eruptions like Toba's, which nearly erased our kind, fit into this larger story. They test the limits of survival, shrinking populations, forcing adaptation, and leaving permanent marks in the DNA of the survivors. These events do not merely threaten life, they shape it, driving its course in directions that would never have been possible otherwise. To walk on the Earth today is to stand on countless layers of this history. Beneath our feet lie the cooled remains of ancient lava fields, the compressed dust of past skies, and the bones of creatures that could not endure the cycles of change. Every mountain range, every valley, every fertile plain carries some memory of destruction, and with it, the quiet miracle of renewal. When scientists speak of super-eruptions, they do not only measure the ash and lava, they speak of thresholds, of moments when the balance of life shifted. For the Earth, these cycles are simply part of its breathing. For life, they are turning points, endings that clear the way for beginnings. In this way, the planet resets itself again and again, carrying forward the story of survival into forms no one could have imagined. The story of the Toba eruption is not just one of fire and ash, nor only of the silence that followed when the skies dimmed and the winds carried dust across the continents. It is also the story of us. For every person alive today carries within them a thread that stretches back to those who endured that ancient trial. Our ancestors faced a world where the air was heavy with ash, where harvests failed, and where the cold pressed close even in places that had once been warm. Yet in those shadows, scattered groups of people found a way to survive. When we look at the world around us now, It is almost impossible to imagine how thin the line of humanity once was. Some scientists believe that the number of surviving humans may have fallen to only a few thousand. Entire languages, entire families, entire ways of life were lost to that darkness. And yet, from those few who remained, the story of humanity continued. Every smile, every voice, every community today is part of that fragile thread stretched through 74,000 years of history. Think of it this way. Everyone you have ever known, every person who will come after you, descends from those who refused to let the flame go out. They may not have left great monuments. Their names have not been carved into stone or preserved in memory, but their endurance is written inside us. It is carried in our bones, in our blood, in the quiet instructions of our DNA. We are their legacy, whether we remember them or not. The eruption of Toba reminds us that life on this planet has always walked a narrow edge between survival and loss. Volcanoes, ice ages, meteor strikes, and shifting seas have each threatened to bring the human story to an end. Yet each time we have endured, not through strength alone, but through cooperation, imagination, and the ability to carry knowledge forward. The survivors of Toba passed down more than just their genes. They passed down memory, skills, and stories, threads of guidance that carried their children through the long winters and back into the light. When we gather together in moments like this, listening to the slow telling of such histories, we are taking part in something old. For as long as there have been people, there have been stories told by the fire, stories that helped communities make sense of the dangers outside and the mysteries above. These stories connected them, reminding them that even in times of fear they were not alone. And now, across a planet far more connected than theirs ever was, we are still doing the same. So tonight, as you rest and let your thoughts drift, you are sitting at the far end of that long line of survivors. You are proof that they endured, that they found a way to live when the earth itself seemed determined to erase them. Their shadows walk beside you in every moment, silent but unbroken. If this journey has brought you a sense of wonder, or if it has reminded you of the delicate thread that binds us to the past, I would be grateful if you gave this video a gentle like, and if you'd like to continue exploring these quiet mysteries together, please consider subscribing to Simply About Earth. And if you feel like sharing, let me know in the comments where you are listening from tonight and what time it is there. I am always amazed by how far these ripples of curiosity can travel, reaching people in cities, villages, and quiet corners all across the world. For now, let yourself take a slow breath, feel the weight of the day begin to soften. You are part of a story that stretches back farther than memory, farther than history, and yet continues on through you. This is the story of survival, written in the ashes of a supervolcano and carried forward into every heartbeat today. And with that, we close this chapter together, softly, in gratitude for the endurance of those who came before, and in wonder at the fragile, precious path we walk now. Thank you for joining me on this quiet journey through one of Earth's most profound moments. Until we meet again in another story, sleep well and dream of the endless resilience that lives within us all. Good night.